knowledge and inspiration. Welcome one and all. Great transport, their minds connect and perspectives with you. A very good morning, everyone. It's my immense pleasure to kindly come forward for the ceremonial lighting of the lamp. I request Dr. Manoj and our principal, Professor Sanjay Kumar Singh, to please accompany our chief guest for the lighting ceremony. Professor H.O. Butts from PRL Ahmedabad, Professor Veerpal Singh, Chief Proctor and Director, CC's Development of Deputy Director of Center and International Cooperation, Professor A.K. Srivastava from IIT, BHU, Professor Anil Malik from CCS University, Shri Ajay Kumar from DRDO, Dr. Bhanu Pratap from National Physics Laboratory, CSIR.
ऐसे थोड़ा सा हमारे उस साइड में एक बाइक भी हो सकती है ना मैं तो बोलती कि खुद ही घर के आदमी इधर ना आए जब है
The lighting of the ceremonial lamp signifies the removal of darkness and awakening of enlightenment. As the sacred flame shines brightly, symbolizing hope and progress, let's also ignite within ourselves a deep sense of gratitude and pride for our motherland. To honor the spirit of unity, dedication, and national pride that inspires every academic and scientific pursuit, we shall now present Vande Mataram, our national song. Vande Mataram means I go to the mother. I request our student Suraj Gupta to please come and recite Vande Mataram. I request everyone to kindly rise and join in this soulful rendition as a mark of respect and reverence for our nation. Suraj.
Hello. वन्दे मां मलयज शीतला सस्य श्यामला मातरं वन्दे मातरं शुभ्रज्योत्स्नां पुलकित यामिनी फुल्लकुसुमित द्रुमुदल शोभिनी हासिनी सुमधुर भाषिणी सुखदां वरदां मातरं वन्दे मातरम् कोटि कोटि कंठ कल कल निनाद कराले कोटि कोटि भुजे धृत कर कर वाले के बोले माँ तुम अबले बाहुबल धरणी नमामि तरिणी रिपुदल वर्णी मातरं वन्दे मातरम् तुम्ही विद्या तुम्ही धर्म तुम्ही हृदय तुम्ही मर्म त्वं प्राण ह शरीरे बहुते तुम्ही मा शक्ती हृदय तुम्ही मा भक्ति तुम्हारी प्रतिमा गढ़ी मंदिर विहारिणी वाणी विद्या दायनी नमामि त्वां नमामि कमला अमला अतुला सुजला सुफला मातरं वन्दे मातरं श्यामलां सरलां सुष्मितां भूषितां धरणीं भरणीं मातरं वन्दे मातरं वन्दे मातरम् भारत माता की वन्दे वन्दे धन्यवाद
सर स्टैंड से लग रहा है
Respected dignitaries on the dais and in the auditorium. Respected dignitaries on the dais, we are truly honored and thankful for your presence and valuable time. As a token of our heartfelt appreciation and respect, may I now request Principal Professor Sanjay Kumar Singh to present a small token of heartfelt gratitude to our Chief Guest, Professor H.O. Watts from Physical Research Laboratory, Ahmedabad. Now request Dr. Manoj Kumar to kindly welcome our guest of honor, Professor Veerpal Singh from CCS University. So please accept this as a small gesture of heartfelt thanks. I request Professor Diti Rani to welcome our guest of honor, Professor A.K. Srivastava from Indian Institute of Science, Banaras Hindu University. May I now request Professor Prakash Chandra Chaudhary, Dean Student Welfare and in charge of Department of Physics, to welcome our guest of honor, Professor Anil Malik from CCS University, Meerut. I request Dr. Aarti Singh to present a small token of thanks to Ajay Kumar from DRDO. I now request Professor Sanjeev Kumar to welcome Professor Bhanu Tap, Chief Scientist from National Physics Laboratory, CSIR Delhi. Professor Kamla Yadav, please come forward and welcome our principal, Professor Sanjay Kumar Singh, for his consistent support and encouragement. I request Professor Kamla Yadav to please welcome A.K. Sharma ji. Professor Kamla Yadav, please welcome our dynamic principal for his consistent support and encouragement. A big round of applause for our dignitaries who have taken out time from their hectic schedule. This conference aims to create a platform where science meets technology and disciplines merge to create transformative solutions. Now I request the dignitaries on the dais to unveil the book, symbolizing the knowledge we have gained through.
चल रहा है वही बार बार चेक
Great pleasure. I invite the convener of the conference, Dr. Manoj Kumar, to address the audience with an introduction and welcome note.
Thank you, madam. Good morning, everyone. First most, the homage to college founder, Holy Highness, Sri Bhavanand Giriji Maharaj. On the dais, chief guest of the event, eminent Professor H.O. Bansal from PRL Ahmedabad, chairperson, principal of the chairperson of the conference, Professor Sanjay Kumar Singh sir, guest of honor, Professor Birpal Singh sir, CCSU University, Meerut, Shri Ajay Kumar sir, DRDO New Delhi, Professor Abhishek Kumar Srivastav sir, IIT PHU Banaras, DSW, Professor Prakash Chaudhary sir, Professor Anil Kumar Malik sir, Professor Satyendra Pal sir, Chief Doctor R.S. Yadav sir, and all scientists, professors in the field of science, technology and society, as the conference convener, I extend a warm welcome to all. It's my great pleasure to welcome you all to the National Conference on Science, Technology and Interdisciplinary Research, NC Still 2026, in the college premises, 24th and 25th February 2026. The NC Still 2026 is a vital forum for sharing and highlights original and novel ideas, current status, the states of the art, significant advances and futuristic challenges on all aspects concerned to the research and development in the field of science, tech and interdisciplinary research or area. The NC Still 2026 is also intended to be the information exchange of innovative ideas, gathering collaborations for academia, researchers, UG, PG and PhD scholars, engineers and professionals within the area. The conference is also planned to endorse the futuristic orientation and understanding for related industries and government to looking across academic industries, partnership, business strategy and policy and regulations. We are fortunate to have a distinguished group of speakers along with an extensive programs that will foster vibrant discussions, networking opportunities and collaborations among participants. This abstract book we have launched here by dignitaries here is a reflection of high quality contribution we have received from experts around the country. I encourage all attendees to make the most of this opportunity to engage with new ideas, emerging trends and breakthrough innovation in science and technology. Wishing you an enriching experience throughout the conference, and I assure you, you will enjoy the science, tech and interdisciplinary research with defined and systematically patterned throughout the event. Wish you all the best and thank you.
Thank you, Dr. Manoj. With great pleasure, may I now call upon Dr. Professor Satyendra Singh for highlighting the theme, objectives, and significance of today's event. Please welcome Professor Satyendra Singh.
दिख रहा है लेंस से चलाओगे तो दो तरह की दिखेगी। यही तो प्रॉब्लम है।
Namaskar and very good morning to all of you. Respected Professor H.O.Vats, Amicus Professor from Physical Research Laboratory, Ahmedabad.
फोन में आ रही है, इसमें नहीं है।
Honorable Principal Professor S.K.
आप देखो
Singh,
लिंक क्लिक करके देखो।
Chairperson of this conference. Respected Professor Abhishek Kumar Srivastava, I made you an icon of the trade review of the solar physics as a distinguished guest. Professor Anik Malik, a scientific legend in the solar review of the physics from Meerut. Professor Birpal Singh, a noted physicist from Chaudhary Chand Singh University, Meerut, as a distinguished guest.
आ रही है।
Dr. Ajay Kumar,
लिंक पे क्लिक करो।
from DRDO, noted scientist from defense sector of India. Professor A.K. Sharma, the Professor of Ajmer University.
अभी वही कर रहा हूँ।
Mr. Convener, participants from different academic institutions, universities, students, media persons, and ladies and gentlemen. On behalf of the organizing committee and on behalf of the MMH College Ghaziabad, I heartily welcome to you all in this national conference on science, technology, and interdisciplinary research, NCSTR 26, to be held at our college during 24 to 25 February 26. MMH College Ghaziabad is a premier academic institution in Western Uttar Pradesh and established in 1948 by His Holiness Shri Bhavanand Giriji Maharaj, today known as Guru Pitaji Maharaj, with a philanthropic vision to uplift and to enhance the downtrodden society of this region and hence glorified with its name Mahanand Mission Harijan College. It is beyond my capacity to narrate such great regency figure exists beyond horizon. Ladies and gentlemen, Department of Physics started in 1938 and its continuous journey in fostering education at UG, PG and research have achieved several acknowledgeable milestones. Presently, with a very handsome capacity of 15 professors, 9 supporting staffs, Department has produced a number of PhD students and completed several major research projects funded by various government agencies and have produced a volume of research paper of national and international repute. In this region of organizing conference by the dynamic department and dedicated faculty of the physics, this conference on science, technology and interdisciplinary research is the second edition. The aim of this conference is to provide ample space, a platform for science and technology fraternities to exchange their academic ideas and to rejuvenate with science updates. And to the students, especially postgraduate, this conference will convey the end to outclass their scientific personalities. Ladies and gentlemen, for nurturing science in society and to encourage our young generation towards science, we plan to launch 3 Best Science Poster Presentation Award, namely Meghnad Saha, Hargobind Khurana, Ramanujan Best Poster Awards in physical, life and mathematical sciences respectively. 2 Best Oral Presentation Awards, namely S.N. Ghosh and Birbal Sahani in physical and life science respectively. 1 Best Young Scientist Award, C.V. Raman will be awarded. Ramanujan Senior Scientist Award will be honored to the best achiever. S. Chandrasekhar Best PhD Thesis Award will be honored to the best performer. Our jury will decide this. For detail about this, you may contact to the registration desk. मेरा आपसे निवेदन है, जो भी इस कैटेगरी में आप रह गए हैं, वे रजिस्ट्रेशन डेस्क पर अपना नॉमिनेशन कर सकते हैं। आज तक 4 These 2 days of PET-CSTIR 26 comprise with this inaugural session, including very exciting and vibrant talks by the eminent researchers. There are 12 parallel halls, 2 parallel halls for technical sessions, covering 16 inviting talks, 60 oral presentations, 69 online presentations, and 35 poster presentations. Will corroborate about total 26 business hours in 2 parallel sessions in these 2 days. Complete conference will be concluded in Physics Department beside this. For your convenient or physical sessions after this hall will be held in C.V. Raman Hall and Meghnad Saha Hall in Department of Physics. Poster presentation in S.N. Ghosh Gallery in Physics Department, and proper arrow will indicate you about this. NCSTR 26 has signed a memorandum of understanding with the General Publishing House for the publication of peer-reviewed and UGC peer listing. And interestingly, the journal is Digital Object Identifier, probably an issue. Again, I expect in these 2 days of busy schedule, you will learn a lot of science. Ladies and gentlemen, This conference is being organized at a very short hold and with a limited resources. As you know, that we have not state-of-art facilities in the college, yet we are trying to provide you an excellent science environment here. During these 2 days, if any inconvenient cause to anybody, at my end or the organizer committee, I feel sorry in advance. On behalf of NCSTIR 26, I acknowledge the financial support from DRDO, and the organizing team concedes the moral and financial support rendered from the management committee through its honorable secretary, Shri Abhinav Krishnaji. Under his propitious and comprehensive direction, the college is flourishing. The contribution of Professor S.K. Singh, principal of this college, is undoubtedly admirable. Professor Gargi will explain it next. Again, I thank you for being a part of a sorority of science, and welcome to you all again. Jai Hind.
Sir, now I invite our respected principal, Professor Sanjay Kumar Singh, to deliver a welcome address.
आज के इस राष्ट्रीय सेमिनार में हमारे बीच उपस्थित हमारे मुख्य अतिथि के रूप में प्रोफेसर H.O. वत्स जी, साथ ही विशिष्ट अतिथि के रूप में हमारे मध्य उपस्थित प्रोफेसर वीरपाल जी, जो कि सीसीएस यूनिवर्सिटी से हैं और रिसर्च डायरेक्टर सीसीएस यूनिवर्सिटी में हैं, श्री अजय कुमार जी जो डीआरडीओ से हमारे बीच उपस्थित हैं, प्रोफेसर अनिल कुमार जी जो सीसीएस यूनिवर्सिटी से एक्स हेड रहे हैं फिजिक्स डिपार्टमेंट में, प्रोफेसर A.K. श्रीवास्तव जी जो IIT PHU वाराणसी से हमारे बीच उपस्थित हैं, प्रोफेसर अशोक कुमार जी जो हमारे बीच उपस्थित हैं, साथ ही प्रोफेसर प्रकाश चौधरी डीन MMH कॉलेज, प्रोफेसर रविंद्र जी और इस राष्ट्रीय सेमिनार के संयोजक मनोज कुमार जी, सत्यपाल जी और सारे मेरे साथी बाहर से पधारे हुए हमारे अतिथि, रिसर्च स्कॉलर और स्टूडेंट्स। मैं इस 2 दिवसीय सेमिनार में सभी का हार्दिक स्वागत और अभिनंदन करता हूँ। 2 दिन ये कार्यक्रम चलेगा। जैसा कि प्रोफेसर सत्यपाल जी ने बताया कि जो टेक्निकल सेशन रहे हैं उसमें साइंस, टेक्नोलॉजी, इंटरडिसिप्लिनरी रिसर्च के ऊपर आप अपने जो है पेपर आप प्रेजेंट करेंगे और मेरा ये उम्मीद मैं करता हूँ कि इन 2 दिन के सेशन में जो इसका आउटकम जो आएगा वो आने वाले समय में रिसर्चर्स के लिए लैंडमार्क का काम करेगा। और मैं पुनः सभी अपनी डिग्निटीज़ का जो डायस पे हैं, जो सामने हैं, हृदय से इस गुरु पिताजी महाराज के परिवार में उनका हार्दिक अभिनंदन करता हूँ, स्वागत करता हूँ। बहुत बहुत धन्यवाद।
We are honored and privileged to have Professor Hariom Vats from Physical Research Laboratory as our chief guest. Professor Vats is a distinguished scientist from the Physical Research Laboratory, Ahmedabad, one of India's premier space and atmospheric research institutes. His research contributions in space science and atmospheric physics have significantly enriched scientific understanding in these advanced domains. I now request Professor Vats to say a few words and formally bless us.
पर बैठे हुए डिग्निटरीज और माननीय साथी और प्यारे विद्यार्थियों, स्कॉलर्स, मैं सब प्रथम आप सबको प्रणाम करता हूँ और कॉलेज के प्रिंसिपल और समिति इस प्रोग्राम के ऑर्गेनाइजर पाल सिंह, सत्येंद्र पाल सिंह, मनोज कुमार जी और उनके साथियों को मैं धन्यवाद देता हूँ कि उन्होंने मुझे यहाँ पर निमंत्रित किया, बुलाया और मुझे कुछ बोलने का अवसर दिया। तो ये मेरे लिए बड़ा एक सौभाग्य की बात है। और जो कॉन्फ्रेंस का स्कोप और थीम जो प्रोफेसर मनोज और प्रोफेसर सत्येंद्र पाल जी ने बहुत अच्छी प्रकार से बताया है, मैं तो यही कहना चाहूँगा कि साइंस केवल पढ़ने या पढ़ाने की वस्तु नहीं होनी चाहिए। ये साइंस जो है हमारे जीवन का पार्ट होना चाहिए। वी शुड लिव इन ए साइंटिफिक मैनर। जो भी हम काम करें उसमें हमें साइंस दिखनी चाहिए। और साइंस के की सोच हम हमारे देश में तो बहुत पुरानी रही है, बहुत पहले से बहुत उन्नति हमारे देश में की है। हमारे धर्म ग्रंथों में भी बहुत सारे ऐसे विवरण हैं जो आज बड़े बड़े टेलीस्कोप द्वारा देखे जा सकते हैं, पर हमारे ऋषि मुनियों ने वो पहले ही बिना किसी टेलीस्कोप के, बिना किसी ऑब्जर्वेशन के अपने योग शक्ति से, अपनी ध्यान शक्ति से उनको जाना था। जैसे उसका एक बहुत सरल सा उदाहरण मैं आपके सामने प्रस्तुत करना चाहूँगा कि अरुंधति वशिष्ठा, ये एक तारा है, सप्तऋषियों में से एक है और ये आज के टेलीस्कोप द्वारा पता लगता है कि ये दो तारे हैं, बाइनरी स्टार है। सप्तऋषियों में केवल एक ये ही बाइनरी स्टार है, जिसका हमारे धर्म ग्रंथों में बहुत पहले से विवरण है, जबकि तब दुनिया में, न हमारे देश में न दुनिया में कहीं भी कोई टेलीस्कोप नहीं था और टेलीस्कोप के द्वारा ही उसको बाइनरी स्टार की तरह से देखा जा सकता है। और दूसरी विशेष बात उस स्टार की ये भी है कि इसका जो बाइनरी सिस्टम है, नॉर्मली बहुत सारे बाइनरी स्टार देखे गए हैं टेलीस्कोप के द्वारा हमारे आकाश गंगा में और उसके व्योम बहुत सारे बाइनरी स्टार होते हैं, पर ये एक रेयर बाइनरी स्टार है जिसमें दोनों जो इसके युगल हैं, दोनों जो तारे हैं वो लगभग समान मात्रा वाले हैं, समान मास वाले हैं और वो एक दूसरे का या दूसरा पहले का चक्कर नहीं लगाता, वो दोनों अपने सेंटर ऑफ मास के में चक्कर लगाते हैं। और उत्तर भारत में तो ऐसी प्रथा नहीं है, पर दक्षिण भारत में आज भी उसको वो मान्यता है कि जब लड़के और लड़की की शादी होती है तो उनको ये अरुंधति वशिष्ठा तारा देखने के लिए बोला जाता है, तो वो तारा देखो। और देखने का जो महत्व है वो वास्तव में ये महत्व है कि पति पत्नी जो दो एक होते हैं, उनमें ना तो पति को ऐसा होना चाहिए कि वो पत्नी के चारों तरफ घूमे और ना पत्नी ऐसी हो कि वो पति के चारों तरफ घूमे। दोनों मिल करके अपने जीवन को आगे बढ़ाएं, संसार को, देश को, समाज को प्रगति प्रदान करें। इसलिए वो तारा देखने की बहुत पहले से व्यवस्था है और उसी से पता लगता है कि बाइनरी स्टार की महत्ता हमारे ऋषि मुनियों ने, हमारे ध्यान योगियों ने कैसे उस समय पर जान ली थी जब कुछ भी नहीं था, कोई चीज नहीं थी। और मैं बहुत ज़्यादा समय ना देते हुए बस ये दो बातें कहूँगा कि जो आज का सेमिनार जो आज शुरू हो रहा 2 दिन का, ये बहुत ही अच्छा है। इसमें जैसे मैंने देखे पेपर बहुत प्रकार के, बहुत सारे मल्टीडिसिप्लिनरी रिसर्च पेपर्स हैं और इसमें विद्यार्थियों से विशेष एक मेरा आग्रह है कि इसको केवल ऐसे ही कैजुअल ना ले, इसमें प्रश्न पूछें, समझने का प्रयास करें और उसको अपने काम से, अपने भविष्य से में क्या आप करना चाहते हैं उससे मिलाने का प्रयास करें और ये कॉन्फ्रेंस कोलैबोरेशन को जनरेट करें और आगे भविष्य के कार्यक्रमों को निर्धारित करें। इन्हीं शब्दों के साथ मैं इस भव्य कार्यक्रम का इनॉग्रेशन करता हूँ। धन्यवाद।
Thank you, sir, for the insightful and thought-provoking address. Your words have truly set a tone for this conference. It gives me immense pleasure to introduce our distinguished speaker for the plenary lecture, Professor Birpal Singh, former head Department of Physics and the Doyer of CCS University, Meerut. He is the chief proctor and has held many administrative key roles, including Director of Research and Development and member of the Steering Committee for NEP 2020 implementation in Uttar Pradesh. With international experience as visiting professor in Japan and Raman Fellow in the USA, he has published over 85 research papers and holds 8 national patents, inspiring countless students and researchers. His research in thin films, nanomaterials, and energy devices has significantly contributed to scientific advancement. Sir, we are truly honored by your presence and eagerly look forward for your keynote address. Please welcome Professor Birpal Singh with a huge round of applause. I now request the guests to please sit in the front row.
थैंक यू प्रोफेसर गांधी। आप सभी को मेरा नमस्कार। आई थिंक पोलर माइक तो चलेगा, पॉइंटर दे दीजिएगा बेटा, ये लाइट बंद कर देना, पीछे की ऑन कर लो। पीछे की तो ऑन कर लीजिएगा। So, very good morning to one and all. Gathered in this important event organized by MMH College, Ghaziabad. I know most of the participants or the organizers who are organizing this particular conference. I'm not going to name their names because there is a shortage of time, and I have to speak something all about the event, all about the organizer, especially Manoj Kumar and Professor Vas has mentioned that that kind of particular events really give some scientific input and output both. In addition to that, that kind of conferences really works wonderfully for networking and some collaborative works. So from that point of view, I will speak on that kind of title on my research related activities at my university. But in addition to that, slide change after next. So I will focus basically on this kind of content in my talk. At very first, I will let you know something all about the university, that the Chaudhary Charan Singh University there. And you are here at MMH College, Ghaziabad. But MMH College, Ghaziabad is very much part of Chaudhary Charan Singh University, Meerut. And being the director of research at Chaudhary Charan Singh University, Meerut, it's my moral responsibility just to connect both institutions, as it's a accredited college of the university. and say something about the achievements especially and the facility available for research at Chaudhary Charan Singh University, Meerut. So in few slides very quickly, I will say something all about the university. Then I will say something all about my research activities which I am carrying forward at my institution with my research students. And then I will let you know some examples of my research. At Chaudhary Charan Singh University, I am working on number of research activities, and I am working with gas sensor, on photocatalytic activities, on energy storage devices, and many more. So in this particular talk, I will highlight only the gas sensor. This is all about the location of the university, although it's not important for you people because it's a national concept and you all know the geographical location of the university. This is all about the recent advancement of the university. And it's my humble request to you all, because you all are the stakeholder of the university. I'm not saying that you all are the stakeholder of the college. I am saying big thing than that of you are all the stakeholders of the university. So from that point of view, try to see the recent advancement of the university. Here I have highlighted that this particular university is NAC A++. And it's a matter of proud for me just to disclose that we are having 3.66 CGPA out of 4. That's really remarkable. In addition to that, we have received Clarivate India Research Excellence Award 2023. And you will surprise to know that Chaudhary Charan Singh University was at the top among all state universities of the country and received that award. In addition to that, we are doing very good, even not in academics, not in research, but we are also doing wonders in sports also. And you may see that we were in 2024, we were at 17th position in country and we were at first position in Hello India in our country. In addition to that, this is all about the university profile and the quality research. And this particular slide may be very important for you people. In the history of the university, under the leadership of our Honorable Vice Chancellor, Professor Vida Shukla ji, we received Times Higher Education ranking, DAR ranking. It's very prestigious ranking. Professor Vas is here, Professor A.K. Sharma is here. They may realize, or you all are academician, you may also realize that in the history of university, we are having that kind of ranking first time. And you are seeing here ranking that the rank band 12012 to 1500. My fellow colleague Professor Anil Malik is here. We all are working hard over there. That's why we are having that kind of ranking. In addition to that, just simply saying that we are having DAR ranking and at the first time, I personally feel doesn't make any sense. Until unless you don't know that what all about this ranking, how prestigious is this ranking, and in addition to more again, that what are the minimum requirement just to apply in this particular ranking. You will surprise to know, just to apply in this ranking, you have to meet 3 major important criteria. And the very first is that your institution should have more than 1,000 Scopus Index paper in last 5 years. And I am sure you know that how difficult it is. More or less 80 to 90% institution doesn't qualify that criteria. So that is so prestigious ranking, and we are having. And I am saying not we are having, you are having, because you are teaching at MMH college. But the degree students are sitting over here. They are holding the degree of Chaudhary Charan Singh University Meerut. So they should build the confidence that they are in good hands and they are holding a degree of a good university. That's a star in IBFA. Second thing, in the history of university again, we are having an NIRF ranking. NIRF. We all know every year this ranking comes, and in the history of university last year, we are at 41st position among the state university category in the country. And again I am saying 41 we are having. What does it mean? If you don't know that there are more than 500 universities under this category, तो 500 में आप 41वें नंबर पे हैं, you will realize it. So it's again a very big achievement of the university. In addition to that, nowadays people are working more all about in STEM, science, technology, engineering, mathematics. And in that category, again, the first time in the history of university, we are having STM ranking surprisingly. Although we don't know that how that comes, because we have not applied, they automatically take that data, and we are among 200 universities of the country, where there are having more than thousands of universities. So we have that kind of achievements in our university. In addition to that, we are also having at rank. It's again a very wonderful ranking for research, because this particular conference is devoted to mainly the research, interdisciplinary research. So you have to realize this particular ranking also. In this particular ranking, you are seeing that it's the SIMAGO institutional ranking that has been given by Elsevier Science. We all know Elsevier. And then in that case, you are seeing how fast we are growing. In 2022, we were at 70th position in the country. I'm saying. Again, in 2023, we were at 66th position. And in 2024, surprisingly, we worked hard again, and we achieved 35th position in the country, and we, increased 31 steps only in a single year, and there was no university, I tried to find out that had that kind of height, only in 12 months. We achieved that. And right now, in 2025, we are having 29th rank in this category in SIMAGO institutional ranking in the country. It's again a very wonderful, achievement of the university. We all know India today. We used to read the magazine of India Today, MDRA. So in this particular ranking, our university, you may realize that now in 2025, we are at 17th rank in this particular ranking, India Today and MDRA ranking. And it's again a matter of proud for me just to discuss with you people that we are at top most among state universities in Uttar Pradesh that providing best infrastructure and learning experience and personality and leadership development. We are at top, and the number of alumni are sitting over here. Mr. Kuldeep is our student, and it's again doing very good, very wonder. And that's just because of that kind of leadership we have inculcated. Maybe I'm thinking somehow like that. Just because of that, we are having that kind of alumni group in with our university. So we were at top in that category. In addition to that, in the research, the next thing is the IPR. So in case of IPR generation, our university is doing very wonder. Last 2 years, we are government university of the country among top 5, and as a consequence of that, we received IPR chair by Ministry of Commerce and Industry, and Chaudhary Charan Singh University was the only university among the state university category that had holding that kind of IPR chair, just because of that kind of IPR generation. As I mentioned that we were at top 5 among last 2 years. So we are having IPR chair. Next. In addition to that, that was somehow all about national and international kind of ranking. In addition to that, Chaudhary Charan Singh University is doing very good in QS ranking also. In QS ranking, you are seeing that our position is very, very good. We are having a rank band in Asia that is 701 to 750, and our Southern Asia rank is 222. And it's again very important ranking. If you go through with that QS ranking, then you will realize that how wonderful this particular ranking is. Next. As a consequence of that kind of achievements, Government of India identify our university under MERU, and we received a grant of 100 crore by Ministry of Education, Government of India and State. And again in that case, I can submit that was the hard work of all the faculty members who are working over there day and night in producing that kind of good research and that kind of good idea. These are our collaborators, national and international collaborators, and this particular institution is our institution. So it's not mentioned to mention the name of this particular institution in this list, because you are very much part of Chaudhary Charan Singh University, and that was the only reason just to realize you people that you are associated with a very good university of the country, that's the Chaudhary Charan Singh University. This is all about the thing or the process or simply how we work. So you may realize that in that case I have tried to mention that we all are working with some definite policies, with some definite rule and regulations. We are having a number of policies, research and innovation policies, and ultimately the number of policies I tried to highlight in this particular slide, that we are working day and night on that kind of policies and try to achieve the heights of our university. That was all about the Chaudhary Charan Singh University Meerut. I am from Department of Physics of this particular university. So it's my moral responsibility to say something about Department of Physics. So this is all about, although there are a number of physics professors of different colleges are there, they all know, they visited this particular department a number of times. They all know, but just for the students, just to attract them, it's my moral responsibility to say something about the department. So we are having that kind of particular courses and that kind of facilities in our department. We are having a very good setup for characterization of material, and we are having AFM, and it's very versatile equipment in our university, especially at Department of Physics. We are having SEM, scanning electron microscope in our university, and that was, the grant was awarded by Ministry of Science and Technology for this particular equipment. Next, we are having RF-DC magnetron sputtering system for research, just for deposition of thin films in our university, in our department. Next, we are having a very wonderful facility, that's a class 10,000 clean room for micro and nano fabrication facility we are having in our department. We are also having smart materials and sensor laboratory at Department of Physics of Chaudhary Charan Singh University Meerut. We are also having solid state crystal growth facility, just to grow crystals for many applications, especially for superconductors, etc. We are also having number of new visible spectrophotometer. We are having micro-resonance spectrophotometer. We are having electrochemical workstation just for characterizing the materials for different applications. In addition to that, we are having a very wonderful setup for gas sensing, on which I will try to show some slides for my research activities. We are having gas sensing setup in our university at Department of Physics. In addition to that, we are also having photonic and metamaterials laboratory, and this particular laboratory is led by Professor Neempal Malik, and that was again funded by Ministry of Science and Technology. And the beauty of that particular laboratory is that this particular laboratory has remote access. Even you can access this laboratory 24/7 across the globe at any place of the globe. So we have that kind of facilities at our university. So that was all about the facilities available at Department of Physics, just for networking, just for collaboration, and I'm not saying I'm saying your research and academic achievements of the university, which you may realize that university is doing well. So that was all about that. Now come to the second part of my talk, and that is all about nanomaterials. I will speak somehow all about nanomaterials just for new researchers, for MSc or BSc students, just to have some exposure all about nanomaterials. So I will speak all about on nanomaterials, and the key issues or the key points of nanomaterials is that your materials having size, shape, and orientation depending properties. So I will highlight these in the next two slides. And this particular talk, I will speak on nanomaterials. So students may realize that what happened with nanomaterials, or what kind of remarkable properties one can achieve, and how your properties may depend upon size, shape, and everything. That kind of realization students may take from this particular slide. And in this particular case, I mentioned that nanoscience and nanotechnology is highly interdisciplinary, and it's not a matter of only physicists, it's not a matter of chemist, and it's not a matter of geologist or life scientist. In that case, you can say nanoscience and nanotechnology are truly interdisciplinary, and the theme of this conference is interdisciplinary research. So you will realize that nanoscience and nanotechnology is again a truly interdisciplinary kind of activity, and that is giving together physics, chemistry, and biology, and many more. And in that case, I used to mention that benefits flow both ways in that case. It's not only the benefits for physicists or chemists or for life scientists or medical practitioners. Benefits flow both ways in that case. And in this particular slide, I try to highlight that how property change when we have a transition from polymer to nanomaterials. And on the extreme right, I try to mention that the material's property may entirely different. As you may realize, one important property that I have mentioned all about the gold, because gold is very important material. And we used to see that what about the rates of that particular material. So you may realize that the gold in general we assume, and chemistry people are sitting over here, that that doesn't behave any catalytic activity. But this particular gold may behave as an excellent catalyst when you have a transfer from bulk to nano at certain definite conditions. One can realize. Even we people being physics scholars used to use number of materials in the category of semiconductors. In case of semiconductors, your band gap may enhance. I have mentioned that. So that is all about that. In addition to that, one wonderful application of material in case of magnetic material is the paramagnetic material. Your paramagnetic material may become super paramagnetic. And just to say in a single line that they become super paramagnetic, again, doesn't make any sense until or unless we don't realize that what kind of change in the properties will be over there. So you will realize that in that case, they have high saturation magnetization. And even they have no resonance MR value is 0. And just because of that, that kind of materials have very wonderful application, not only in magnetic recording, but in ferrofluids, in imaging, in magnetic separation, and even with the treatment of very dangerous disease, namely the cancer. So that kind of realization one can have, that how property will change. This is all about the different nanostructures, how they form, and you can say how you can confront the dimensions of that kind of materials. I try to highlight for beginners that you may have different kind of nanostructures and their name will be as per their geometry. And just for fabrication, we may have two kind of approach. The one will be the top down, and second will be the bottom up. I try to highlight only that. Next. This is all about the real research practice which we are doing at our university. And here I try to mention that we are mostly working on semiconductor materials with lot of number of applications. And here I try to highlight only one application, that is on sensing application, especially on electrochemical sensing and for gas sensing. So in general, I may conclude that we all, either we are doing chemistry or we are doing physics or we are doing astrophysics, we all are dealing with materials. And in that case, the utilization of any kind of material, that may be of your food material, even that may be of your clothing, that may be your transportation material, that may be of your IT material. The utilization of material is purely a selection process. So from that point of view, you may realize that what kind of materials you are selecting for your research. In my research, we mainly focus on semiconducting material, especially for electrochemical sensors and for gas sensors. This is all about a very important material. I am now discussing all the property of this material, and that's the iron oxide. And this particular material has number of phases, and it's very difficult in the synthesis of iron oxide just to control the exact phase of the material. Chemistry professor may realize that how tricky is just to control the phase of iron oxide. So in our research, we absolutely control the phase of this particular material, namely iron oxide, with alpha and gamma phase, and use that particular material for sensing a very wonderful drug. You all know that, that's the acetaminophen, which you used to say the dolo, the calpol, or the paracetamol. So we sense this particular drug by using this particular material, iron oxide. And again, all about iron oxide is that iron oxide is biocompatible with our body tissue. So this particular material is very useful for sensing drug molecules maybe in near future in pharmaceutical industry. This is all about that we sense this particular drug, Alcohol, and in US we used to say that Tangalon by using iron oxide nanoparticle. This is all about the synthesis of that particular material. We synthesize this particular material by using simple chemistry, by precipitation method and all you are seeing over here, and then we characterize the material by number of techniques, by using XRD and all, and we calculate the particle size. And then we confirm that the material is in exact phase, and by this TGA and DSC analysis we can conclude, or by Raman spectroscopy we can conclude that our material was in desired phase, and that was alpha phase of iron oxide. Move forward, and ultimately we modify the classic carbon electrode of electrochemical workstation by our material, that was iron oxide nanoparticle, and successfully sense this particular drug. Is very important, you know all well, by using electrochemical sensing. This is all about the research results at different concentration of acetaminophen, and we ultimately reach more or less up to 10 to power minus 6 molarity of the concentration by using this particular technique. Come forward. In addition to that, we again sense a second molecule, drug molecule, that is hydrogen peroxide. We also sense, and research going on this particular molecule, and these are some primary results. Move forward. Of sensing, and we successfully sense this particular drug by using iron oxide. In addition to that, we have good publication by using that kind of research. Move forward. We publish a number of review articles, and for researchers who are working on electrochemical sensor for drug detection, maybe this particular review article, because this particular review article has a lot of citation, people across the country, scientists across the globe are reading this particular research article, because in this particular research article we review all the things all about the electrochemical sensor for drug detection using nanostructures of all kinds. So that particular research article is very useful for research. Move forward. This is all about the gas sensors, and this is all about the physics, how the response of the sensor change, and that change as far as the nature of gas is concerned, and as far as the material nature is concerned, either your material is of N type or P type. In this particular research, we sense hydrogen, because again, hydrogen, sensing of hydrogen, production of hydrogen is nowadays very important part of any research, because hydrogen is a clean source of energy. And you are again reading number of news all about the hydrogen production as well as hydrogen detection, because hydrogen is a wonderful source of energy. In that case, we simply detect or we simply sense only the hydrogen in our research by using PD-CAM carbon, copper oxide, thin film, which we deposited by sputting technique. This is all about the basic results, XRD, XPS, the SAM, all and all. I'm not going to discuss all about the details of that. And we publish, this is all about the sensor characteristics of our CU, your PD-CAM copper oxide and thin film for hydrogen sensing. And in this particular case, we sense hydrogen at ppm level. And we published this particular article in a very good journal, Journal of Electronic Material, and this particular work has been done. One of my friends is sitting, Mr. Prasad Yadav, who is working at Padot, and that wonderful work he produced in PhD. The second thing in this particular material, we use MOS2. MOS2 is again a very wonderful material. It's 2D material. Go fast. And in this particular material, you may realize the general application of this particular material, and that may be the substitute of graphene in general. And that particular material may be very useful for energy storage, for electronic device, for biomedicine, for sensor, even for photocatalytics and electrocatalytics. So that particular material has wonderful application. In our case, we particularly deposited MOS2 thin films by using this sputtering. And first time, as far as literature survey is concerned, we deposited MOS2 thin films by using reactive sputtering by simply using the molybdenum target. And our reactive gas we use, that was the hydrogen sulfide. So this is all about the motivation of this particular work. Move forward. And in this particular work, we sense NO2 gas, because NO2 is a very hazardous gas and it's the air pollutant. And you may realize that how badly that effect, starting from our eyes to skin to kidneys to all and all, badly affect our body. So we try to sense this particular gas by using MOS2 sensor, which we deposited in our department by using sputtering technique. This is all about the sputtering which we have at our university, and we deposited, and this is all about the deposition parameters of MOS2, and ultimately we deposited good quality thin film having high surface area by using sputtering technique. And this is all about the characterization of that particular kind of material. This is all about the nanostructures, and that was of nanobombs kind of structure over there. And give you the name of that kind of structure, nanobombs. More quickly. This is all about the different characterization of that particular kind of material, thin films, MOS2 thin films, and ultimately we use that particular kind of, we functionalize that particular material by using again by copper, just to have more active sites in our thin film. In one line, I can sum it. And ultimately, we functionalize this particular MOS2 thin film by using copper and use that particular thin film for sensing your NO2 gas. This is all about the EDAX system and just to confirm the composition. This is all about the XPS, this is all about the optical spectroscopy and all about the PL. And this is very important. This is all about the gas characteristics of our sensing characteristics of NO2 with our CU functionalized MOS2 thin film. And this is all about again the characteristics, gas characteristics, sensing characteristics. And again we publish this particular results in Royal Society of Open Sciences. And ultimately we sense hydrogen oxide, and as a result we publish number of papers on as a review article as well as original research article on CU functionalized MOS2 thin film deposited by sputtering technique. We also obtained one patent, although I have number of patents in my name, but one patent I report only on MOS2 structure, and we deposited MOS2 as a nanocactus. Nanocactus type of material deposited in that case, and we got patent on that. This is all about the acknowledgement, and this particular work is supported by CSIR, by our university, by NRFT, and by the collaboration of ITP. So with these words, this is all about my research group, my friends, and they got awarded their PhD on that kind of work. So with these words, I may conclude all about my research activities, although I have not discussed in-depth kind of analysis of my research because time was short for this particular lecture. And I try to highlight that what really we are doing at our university, especially at Department of Physics, as far as research activity is concerned in my research group. So with these words, once again, let me thank the organizers, especially the principal of this college, Professor Sanjay Singh ji, and the organizer, Professor S.P. Singh ji and Manoj ji, and all. I am not naming. One of my classmate, Dr. Pavna Yadav is here. He is again the member of organizing committee. She received well in the morning. So thank you very much for listening me patiently. And I try to realize what kind of activities we are doing at our. Thank you very much. And quickly, I may take some query very quickly if you people have related to research activities especially which we are doing at our university. So with these words, once again, thank you. चाहते हैं तो वो बात कर सकते हैं, अदरवाइज तो प्रोफेसर को उनको पूछते नहीं है, उनसे तो हमारी बात हो रखी है, उनको सब आता है तो वो तो नहीं पूछते. Anyhow, students may ask if they have some query all about the research activities which I try to highlight only highlight, which we are doing at our university. So thank you very much.
you very much, sir, for sharing your valuable insights and expanding our horizons. We are proud and privileged to be part of Chaudhary Charan Singh University. And I'm sure many of us have got the inspiration to do a lot of work in research after listening to the good research from Professor Vipal Singh. Dr. Anand sir is amongst us. I extend a very warm welcome for your presence, sir. Professor A.K. Srivastava is a respected professor at Indian Institute of Science, Banaras Hindu University, Varanasi, with remarkable contributions in the field of physics. Through his dedicated research, teaching, and academic leadership, he has made significant contribution to higher education and scientific advancement. We warmly welcome him to the conference, and I request him for his experience and research.
Yes, yes. माइक ठीक करना पड़ेगा जाके.
My colleagues are still downloading here. So basically, I am Abhishek Srivastava. I am from Department of Physics, Indian Institute of Technology, Banaras Hindu University. So here, Professor DPC, he was talking about nanoscales. He was talking about the matters and nanoscale, and I will take you towards some planet scale where some different physics is being involved, and that is basically the megameter scale scalar objects and plasma systems. Just wait for a minute. So, this is my slides are running here. So as I said, once you talk about nanoscale physics, so you can see lots of things there. But once you go to the megameter scale, in astrophysical objects like sun, so you find out some spectacular classical physics and physical physics. So you can see here the detail. So what you see in this animation, that is the real observations, and these real observations are captured from a very fine observatory of recent days, and that is known as solar orbiter. And over the solar orbiter, there is an ultraviolet telescope which is observing the sun in such a greater distance. As I was saying, that the Singh was talking about nanoscale physics and realism. And here, what you are seeing here, they are basically the plasma. And you can see, this is the atmosphere of the sun. And this atmosphere is totally made by the plasma and magnetized plasma. Here, the title of my talk is the symbiosis of waves and energy. So it looks like a mechanical, but probably you can connect yourself by this word, symbiosis. I think there must, you remember this word, symbiosis. Symbiosis is studied in high school classes for living systems, where the two systems were living on each other, their life were depending on each other. And we are employing or discovering some ideas in solar plasma and in context of magnetized plasma, where
two physical processes which are known as waves and magnetic reconnection process. They are supporting each other and they are showing the symbiotic. It looks too technical, but believe me, this is very easy. So I'm going to take you to the true love sun, and thank you sir for your presence here. Professor was a senior solar physicist, radio physicist, and we all seen him since our student life when we are doing PhD. So your professor presence is here sir, and I'm going to discuss something. Can you switch off? Okay, so now you can see here. Before going to the sun, just I want to take a kind of compliment here, and this is not my statement, but this is proposed by Nobel laureate Hans Alfvén, and he basically proposed that plasma constitutes 99.99% of the physical universe, and there everything is in plasma state. But you are aware of the plasma. So you can see here, sun is made up of plasma, binary stars are made up of plasma, and even the planetary magnetosphere like Earth's outer atmosphere, that is made of plasma. And not only the astrophysical systems, but you can see here, the laboratory is having plasma experiments, many fusion devices, industrial applications, related plasma devices, they confine plasma, they use the plasma for different purposes. And I am happy to tell that most of these experiments, they take the example from the astrophysical plasma system. So basically, these are the systems which are very large scale plasma systems, and you are aware that plasma is nothing but, can you go back? So plasma is nothing but the state of the matter. Maybe you could call it the fourth state of the matter, but basically there's a peculiar state of the matter which is formed by the ions and electrons, and it shows some peculiar behavior like quasi-neutrality and collective motions and so on. I'm not going into the details of those things, but Langmuir was the first who pointed out this word plasma. And as I said, the most of the objects in the universe are made by plasma. But here, we will emphasize the science which is related to the sun. Why sun? We must compliment that in the whole universe, there is only one object, and that is our planetary star, which can be observed in a greater detail using space-borne observatory, using ground-based observations and telescopes, okay, and no other object. So if you want to understand any similar object at its physical state in the universe, we used to go to the sun and try to understand its plasma processes. And even if you want to do the experiment in the laboratory, so we always take the examples of the physical processes at the sun. So sun is the central point. That is very important for us. So here, this is very general description. You know, this is the sun, this is the artist image of the sun, and this is the interior part of the sun, where this is core, where nuclear fusion takes place, hydrogen bonds, the 4 proton compounds, and they generate energy and helium, plus other products, and that energy propagates in form of gamma and X-ray photons, and they cross the radiative zone, they reach to the convection zone here, and then they transport it up to the surface of the sun or similar kind of stars, and the surface is known as photosphere. Similarly, the magnetic field is generated by the dynamo axle, and that magnetic field is transported over the surface by the magnetoconvection process, and many other complex dynamics which is happening in the interior of the sun. And once magnetic field and plasma appears at the surface, basically this spans into the atmosphere, and this constitutes basically the other part of the atmosphere like chromosphere, transition region, and the magnetized corona. Now you heard about the corona. This is named as a corona because it has crown-like shape of magnetoplasmic system there. And once you go and see the temperature and density profile in the sun's atmosphere, So you can find out that density is continuously decreasing here, as well as temperature after showing certain increment and little increment up to the chromosphere at the bottom of the transition region, it suddenly enhances very abruptly. So you can find out here that temperature is around 6,000 Kelvin at the surface, but once you move 2,000 kilometers approximately up to the surface, the temperature is basically going to the million degree Kelvin. And believe me, this is one of the outstanding processes in physics and astrophysics, and it is not permanent. Nobody could solve it yet, and we all are trying to understand it by different perspectives. And today I will discuss one of the perspectives, what we are going to make, what we are reporting for the last 6 to 7 years in past. So let's go ahead and see. So as I said, the temperature of the sun's corona is very high. So you can find out lots of highly ionized species there, like you can find out the iron of several times ionized in several times ionized state. And those irons and other species elements which are in highly ionized state, they basically emit in ultraviolet and extreme ultraviolet wavelength. So this image is taken from SUAIA telescope, and this is extreme ultraviolet image of solar corona. You can see lots of structuring in that atmosphere. And this is very famous Yogo X-ray image of the sun, which is taken in the 90s, and you can again find out that sun's atmosphere is not like that. What you see in the morning and evening time, like a very plain type of structure, which is basically the surface of the sun. And one most important thing is there, that sun's atmosphere emits particles, charged particles, stream of charged particles. Basically, the protons, helium, or you can say alpha particle, and other elements. And that forms the stream which is known as solar wind. And you can see here at the pole, the solar wind speed is of the order of 700 to 800 km per second, very fast, 700 to 800 km per second. And near the equator, basically you find out the solar wind that is of the order of velocity 400 to 500 km per second. So you can imagine how gigantic, how powerful, how energetic the sun's atmosphere is, and how it is radiating in ultraviolet, in X-ray, in other wavelengths, as well as how fast it is emanating continuously the charged particles which are formed in the solar wind, and how the solar wind is originated and how fast it is accelerated. That is still a kind of debate. People are trying to propose various theoretical models, lots of observations from Parker Solar Probe recently. They are trying to set the right, but the things are like how this is happening. That is the open question. So coronal heating is one of the open questions, and how the solar wind accelerated, how the solar wind is originated, and how it is accelerated in the interplanetary space and the heliosphere. That is a kind of big question. So these two questions are somehow interlinked with each other, and people are trying to understand the physics behind the exact fact. So I will go ahead and let me explain this. So this is a visual perspective of coronal heating problem. Once you go to the star's core, so nuclear fusion generates a very high temperature, but as per the law of thermal physics, once you go from the source away up to the surface, temperature drops down significantly, and this is very, very nice. No problem at all. But once you go up from the surface within 2,000 kilometer height, that is, we are going from Delhi to Bangalore, the temperature is increasing from 6,000 Kelvin to million degree, huge temperature growth. What is the physical process? That defies basically the laws, classical laws of physics, thermal physics. So there must be something that is what. So we will try to understand that perspective in certain measure. Sir, can you please switch ahead? You see, again, the visual perspective. So this is not just the visual perspective, but this is some scientific measurement. I have done some kind of temperature measurement in the sun's equator. And you see here is the big equator, which is observed by Solar Dynamics Observatory and its atmospheric imaging assembly telescope. And by measuring the differential emissions at different ultraviolet wavelengths, we have somehow diagnosed the temperature. And you can see it's a big scale. Go back. And you can see here the overall temperature is really 1 million Kelvin. This is coronal heating. But one other thing is that it's not the static temperature. It's not always one and thing, but it is a time-dependent plasma system, basically where any kind of energetic activities like the energy release through solar flare that can enhance the temperature, but it is plasma gas. It cools down obviously. And if it maintains for several minutes or several hours and so on, that means huge energy is being required. So you see here, this is a time-dependent plasma system. Lots of energetic processes are working, lots of energy loss mechanisms are working. You have to quantify, you have to diagnose, and you have to measure them. Let's try to go. This is basically the numbers. This is very classical number. So just I want to emphasize, forget about all these technical details, just see the order of these numbers. White sun, where magnetic activity is very small, not very big. Coronal holes are the polar regions of the sun. Generally they appear at the polar region of the sun, sometimes at the equator. Active regions are basically the sunspot groups where magnetic field is very high. It can go beyond 1000 Gauss. So you can see here in the atmosphere how much energy is being required. Energy per centimeter square per second is of the order of 10 to the power 6 Earth. Can you believe how big the sun's plasma system is? Very big. And you know the energy requirement per centimeter square per second, it is 10 to the power 6 Earth. So you can calculate the total energy budget. You can presume how big this problem is and how in a what defined way we should understand it. Okay, sir?
आप इधर ध्यान रखिए ना प्लीज.
Okay. Good. Our district speakers are here. Go ahead.
Sir.
Please. Okay. So you know, key is there. Key is here. You know, once you go and see the visible surface of the sun at temperature 640 Kelvin, 00 Kelvin, you will find out the things like what you see in the morning and in the evening time. You can see here some sunspot groups which are the reason of high magnetic field of the order of 1000 Gauss or more. But you see the magnetic field. This is the magnetic field measurement. And probably you recall where the sunspots are, the magnetic fluxes are very high. White is the positive flux, black is the negative magnetic flux, and you can see here the fluxes are higher where the magnetic sunspots are where they are at the surface. Go ahead. Now you linked with the upper atmosphere. Can you please make a big silence? You see, this is ultraviolet emission, and this is at 1600 angstrom, continuum ultraviolet emission, and here the temperature is 8000 Kelvin, and now you can correlate. We are moving up in the atmosphere, the magnetic field regions, there were those regions which are having more heated plasma, more emissions are there. Go ahead. This is again, you are going into the chromosphere, much higher. You are seeing the chromosphere hydrogen alpha with more high temperature. You see again the activity is at the same place. Please go ahead and you find out the upper atmosphere corona. So everything is linked. Everything is linked. The surface and upper part of the atmosphere are highly coupled plasma system. with the magnetic field and so on. And now go ahead. Go ahead. How we can deal with it? So here is one thing. When we apply the magnetohydrodynamics over the large length scale and time scale where various plasma processes are occurred in the sun are similar offset. So you can apply the magnetohydrodynamics, and everybody is aware that MHD deals with the coupling of Maxwell's equation with the equation of fluid dynamics. So basically we can treat the sun's plasma, the plasma within the sun's atmosphere as a MHD system, and we can treat them as a magnetized fluid, plasma fluid. And you know, this MHD scale can be applied to not only to the solar atmosphere, but to the various astrophysical system and even to the laboratory plasma. And here, I already spoke the reason. Because we have very large length scale, much bigger than the divided length scale, and the time scale of the processes are much larger compared to the inverse of the ion gyro frequency. So the MHD scale is a kind of approximation that can be used significantly, and we can learn what is happening in such kind of plasma systems in different objects, including the sun. So you see the response. This is basically the MHD response of the system. You can see here, if you consider the homogeneous plasma even at the MHD scale, and you consider the solar atmosphere, for example, and if you perturb this plasma system by the periodic driver, and you generate the perturbations in plasma quantities, plasma parameters, as well as magnetic field, so you can generate the wave mostly. And there are three kinds of waves that can be in the homogeneous plasma system. You can see here the physics in a very general manner. The first is slow magnetoplastic wave, and this propagates along the magnetic field lines. You can see the propagation vector is aligned with the magnetic field lines, and this only perturbs the plasma pressure in limited quantities, but it doesn't do anything with the magnetic field. Magnetic field just provides a path. So let's say slow magnetoplastic wave is here in this room, and magnetic field is directed, let's say, towards you, so it can propagate from my side to your side along the field line. And you will be happy to see the observations. You see, this is SGAIE observations, and these observations are telling about the generation of slow magnetoplastic waves. See the perturbations which are following the magnetic field lines. Apart from slow magnetoplastic wave, here are other kind of waves which are fast magnetoplastic waves. And these waves, they can propagate at any angle with respect to the magnetic field, and its velocity is the highest velocity in the plasma system. You should remember the slow magnetoplastic waves will only propagate with the local sound speed, but this wave would be very fast. And probably you are able to see the real observations from SGAIE, and this is done by our colleague Ian Benyu. So you can see the observation. Very fast wave fronts are propagating in the sun's corona, and they are not confined to the magnetic field, but they are moving across the magnetic field line. And another one is very famous. Probably you people are aware, many of you who are studying in MSc, you are aware with the Olfin wave. So Olfin wave is this transverse wave which basically perturbs the magnetic field only, but not the other plasma parameters. So it's a kind of string-like wave which is basically perturbing the magnetic field in transverse direction. This is an incompressible wave, pure incompressible wave, and you'll be happy to see such kind of waves in the solar atmosphere. You can see these magnetic field lines, they are oscillating like a transverse wave. So these are the three wavelengths that can excite in any kind of homogeneous magnetized plasma system, and they are well observed in the solar atmosphere thanks to this high resolution observatories in this space. Now, once we go ahead and see the more fine details. So what we will find out that homogeneous plasma is just a kind of ideal speculation. It's a very kind of ideal approximation. Basically, once you find out the plasma, this is structure. When you go to the sun's atmosphere, or when you go to the other objects, so basically plasma is not very homogeneous. This is structured, and once you find out these kind of magnetic tubes in those atmosphere, so they can generate some other tube waves, and they are known as king wave, sausage wave, and torsional olefin wave. So I'm just introducing these waves, and you can see here what is king wave. King wave is nothing but if you take this plasma tube, let's say it is at the sun's atmosphere, and its length is several megameters, very lengthy plasma tube. So what is happening? The resultant force is working in a manner that this tube is oscillating like this in a transverse manner, and basically this is generating this anti-symmetric, or you can say the axis symmetric waves there, anti-symmetric waves there, where only the tube as a whole is being displaced. The radial component of magnetic field is being perturbed, but density is very little perturbed, so it is almost incompressible wave. You cannot just see them. And here, this is symmetric wave, this is longitudinal kind of wave, which is being created by this pinching and twirling of the plasma system. And this is basically the sausage mode waves. So this changes the tube's cross section, and this is being generated in the inhomogeneous tube. And this is another olefin wave, but it is within the magnetic flux tube. And you can see here what is happening. The azimuthal component of magnetic field is being perturbed, and that is basically being generated. This wave is being generated. So this is the olefin analog of tube, magnetic flux tube, and this is known as the torsional wave. So you see, waves are there in the sun's atmosphere, and these waves are famously known as magnetohydrodynamic waves. These waves have a capability to carry lots of energy into the different parts of the atmosphere, in the solar corona, and even in the far corona, something like that. And when this is being done, so it can generate lots of heating and energy output there. Apart from those waves, here is another exclusive process that always works in different plasma system, and this is known as magnetic reconnection. Probably, when I will say that two magnetic field lines can cross each other, can cut each other, and they can change its configuration, you will tell, okay, you are coming wrong, because you know how it is being done. Because magnetic field is not like that. It doesn't behave like that. But here is not the simple magnetic field. It is the field which is present in the magnetoplasma system, and this is the peculiar state of the matter, you can say. And here it is happening. When two opposite field lines, let's say like this, they are coming closer to each other, what they are doing, they are self-reorganizing. And the stored magnetic energy there is emitted in form of latent kinetic energy. And this is kind of a many flares, many other exotic plasma processes, energy release and heating. So it's not only the theory, it's a very important process which is even seen in the observations. You see, this is the Nature paper, and here in this paper, these groups, they have observed the magnetic reconnection process in the sun's atmosphere. Okay? So, the message is very clear. Sun's atmosphere is very structured. Okay, so you see here, so I think it's very hard to control. It's your system.
Hand control is better.
Okay, do you see? Okay, so message is very clear. Sun is a very exotic concept. It's the right place where you can learn various physical processes which are embedded in the magnetized plasma. You can take away the knowledge about those physical processes. You can apply it to lab scale. You can apply it to other astrophysical scales. But you can also solve the big problems which is related to the sun and Venus manipulation. You have plenty of observations throughout. You can observe the sun, magnetic field. You can observe in X-ray. You can observe in ultraviolet. You can observe the in situ particles, and you can cover from sun to earth. And probably you heard about the Aditya L1. Aditya L1, which is our national mission recently. It is exactly doing the same. It is trying to observe the sun starting from sun's atmosphere, lower atmosphere, using SOOT, Solar Ultraviolet Imaging Telescope, and then it is observing the sun's corona and its X-ray emissions, and then it is observing the outer sun's atmosphere using its coronagraph, and then many in situ energetic particle measurements as well as magnetic field measurements at the L1 point, because Aditya L1 is at L1 point. And all the instruments are indigenous, they are giving excellent data, and we are, and the community is analyzing it, and exclusive signs are coming. These two are one of the great objectives of Aditya L1 mission also. So, let's go ahead and try to see a few examples. So, as I was telling about the waves, you see this is one of our paper in Nature, and here it is never seen before observations. It is made by the biggest telescope on the ground. It is not biggest, but another one from BBSO, Big Bear Solar Observatory. Okay, and you can see here, this is the sunspot. I told you about the sunspot. Sunspot is the region at the sun's surface where magnetic field is very high, of the order of 1000 watts. But here, the magnetic field is of the order of more than 2000 watts. Okay, so you can see here, this is the central part of the sunspot, and what you are observing in high resolution observation, that shockwave kind of plasma perturbations are moving. You can see here this is front. And what they are trying to do, they are trying to interact with magnetic flux tubes, which are very tiny flux tubes. So what they are doing, they are exchanging energy with the tiny flux tubes, which are present like this. And you see what is happening, transverse oscillation is happening. I told about the transverse oscillation just in my previous slide. Okay, this transverse oscillation is nothing but fast magnetocaustic chain oscillation and total energy, and you can find out that this energy is huge. Huge energy is prevalent in these oscillations, and these energies are being transported up in the atmosphere, and this could be the one of the source of coronal heat. So we are giving the solution, okay? These energies are not coming from anywhere outside. It is not coming from interior. But somehow the coupled atmosphere at different scale is generating some wave-like motions, and these wave-like motions are transporting energy. And here we have shown that it is also coming from these small scale tubes which are oscillating by the King wave, and they are throwing the energy passes up in the corona, and they can heat the corona. So this paper we published in Nature. And this is another Nature paper that we published in 2018. And you see here, this paper introduced a novel mechanism which we call as pseudosun. So this is not the photosphere where sunspots are there. This is not the lower atmosphere, but this is the middle of the atmosphere, just below the corona. And you can see here lots of some jet-like ejecta, plasma ejecta shooting up, and its length is 4 megameter, 5 megameter. You can imagine the length, 4, 5 megameter. It's still there, very small and localized, and they are again near the periphery of the sunspot. And once you see analyze them very carefully, so what you will find out that they are not just plasma which is shooting out, but some process is happening. Entire plasma is being sifted along the magnetic field lines, and it is reaching over the top and bulging as a crown, very bright crown. So we found that there is a density jump, and any discontinuity comes in these plasma systems through any perturbation forms basically the shock. But here we could not find the real shock structure, but soft-like structures, and we told that these soft-like structures are basically the pseudosoft, and they are not one, two, or three. There are many and many. So what we found out that if you consider such kind of regions where these jets are propelling up with the pseudosoft, so we modeled them. You can see the model, and this model is very much similar to the observation. And you can see here that these ejecta, they are containing energy, and that energy is sufficient to fulfill the losses in the solar atmosphere. Okay, so required energy is there. So they are the energy source. They are another energy source which can pull the energy, and they can push. They can submit the energy there in the localized corona, and they can cause the heat. So these are our exclusive work about the energy sources that were being published in Nature Astronomy basically, and another one. You see, this is Nature Scientific Report. This is another source, and all their real observations from the world's biggest telescope. Again, this is SST, 2 meter class Swedish solar telescope, and you can see the Swedish solar telescope is observing the plasma tubes which are observed, which are moving like this, and basically this is very much resembling to the torsional wave. I told about the torsional wave. This is the motion which is like this. So this torsional orbital wave is being generated, and not only in the intensity seen, but in the Doppler imaging it is seen, and we have modeled it by our NSG code. And what we found out that these kind of motions are prevalent in the lower part of the solar atmosphere if sufficiently resolved, and they are trying to bring the energy into the upper atmosphere in the corona, and they are trying to keep the corona. So see, we are trying to understand different energy sources, and we are able to find some of them. So we are getting some success in finding some energy sources, but we believe that these are not one process or two processes or something like that, but a very complex suite of the processes are running in the solar atmosphere, in the different parts of the solar atmosphere, and we must explore them, we must observe them, and we must theoretically model them. So here is another exclusive example. So we talk about torsional orbital wave, and it as an energy source. We talk about pseudosoft, we talk about Q wave as an energy source, and those exclusive observations and model. But here, this is another first finding we have made. So I talked about magnetic reconnection. So what is happening? One set of magnetic field lines are reconnecting with the other set of magnetic field lines. They are self-reorganizing, and heating is taking place. Here you can see in the rear of this. You see, this is the sun's equator. Here is the large-scale sun's corona, and you can see this is SGO-AIA observation. You can see here, this set of magnetic field lines are going this way, this magnetic field lines are going that way, and then after reconnection, they are going in this direction. So this is very classical example that magnetic field lines are coming closer, they are diffusing through the plasma, and then they are self-reorganizing, and stored magnetic energy is liberating in form of heat. You can see here, the temperature is rising. So it is energy source, but here is one point, that this is not the spontaneous reconnection, because everywhere corona is not need for this spontaneous reconnection, because magnetic Raman number is very high. So what is happening? Some external driver is setting in, and that external driver is basically forcing that region to be reconnected. And once this forcing up is happening, so we call it forced reconnection. Spontaneous reconnection were being observed in the solar corona in past. You can see the Nature paper, but the forced reconnection, direct imaging of the forced reconnection and its modeling was not available. So this paper and other papers also, that was the part of global media coverage, and basically NASA wrote popular articles on our series of papers, including this one, and it was covered by entire global media, because we are the people who are trying to advance this area, by continuously searching the energy sources and physical processes through the observations and modeling. Okay, so now I will take quickly on these ideas because this is my technical details. So now, okay, fine. So basically, you know, waves could be the energy source, shocks could be the energy source, magnetic reconnection could be the energy source, of course they are energy source. But what happens when they do the symbiotic behavior? And that basically being studied by some of our old pioneering colleagues in 70s and 80s, and okay, I'm going to conclude. It's a very interesting story, actually. So basically, in 70s, there was one Japanese colleague. His name was Professor Sakai. Sir, you know about Sakai? Professor Sakai. Sakai and Kojima. I mean, you are not aware of the name, but that is aware. They discovered in some books something about, you know, what will happen when wave will go to the reconnection region. Nobody could give any kind of attention in a larger prospect, because on that time there were not much observations. Then people started talking about the interaction of waves with the reconnection region, or reconnection regions are generating waves. You please notice, these are the energy sources that can hit the plasma, that can enlarge the plasma. So once we do like that, we can think about such a symbiotic nature. So this is the Indian colleague, his name is Pankaj Kumar. He is in NASA. He was PhD student in his mentor when I was there. So he published a paper in Nature recently, and where he talked about the wave, and this wave is basically trying to interact with this region, which is not a reconnection region, but a kind of singularity where magnetic null exists. And once magnetic null exists, so here we give the similar, not similar, but the proposition of symbiosis. What is happening here? You see, this is the reconnecting current switch, and this is going into the tearing mode phase. This is very technical word, so don't worry about that. Tearing mode phase, and this tearing is basically generating waves. And this wave is going far apart in the solar atmosphere. And if you follow the lower image are the physical process which is occurring in the bottom panel. So you will only observe the waves. Here, what we want to say that reconnecting current switch can generate waves, and we cannot ignore such kind of symbiosis, because the property of the wave and energetic of the waves, they all depend on this reconnection phases of the current. And similarly, we observe, you see here, the wave is trying to move up with certain eruption, and reconnection is being generated here. So I would pass very fast from these things. You see here, the wave is being generated, and these waves are, once interacting with the magnetic null here, they are creating the reconnection region. So this red arrow is basically the Lorentz force, and this green arrow is the magnetic field, and you can see here how the wave, once wave is trying to pass from that particular magnetic singularity, this reconnection region is being generated, and I am quickly passing through these details because they are very technical. You can see here, once this wave is passing through the magnetic singularity there in the sun's atmosphere, there are similar kind of system. So earlier magnetic field was very smooth across that point, but later this magnetic current seed is being generated where reconnection is a predominant phenomenon. And you see, I will skip all these things. Temperature is rising. Temperature is rising. So you see, temperature is rising, and this is how you see in the observation. I will skip these examples, and last message is here. Experiment. So I talked about solar atmosphere, but you see, experiment is also here. And this experiment is not done by us or any Indian group or any American group, but of course it is one group from Russia, and they have done the experiment. What they did, they have made similar kind of magnetic configuration with magnetic similarity, which is known as magnetic null. You know magnetic null. And what they are doing, they are transporting a wave, similar wave what I have shown earlier in solar corona or in the theoretical descriptions. So this wave is being here, and once it is coming there, so this current sheet or magnetic reconnection region is being formed. And you see the scale. The scale is centimeter and time scale is microsecond, and this is pure experiment. So what we are thinking about the symbiosis, we are not alone. Of course, these Russian colleagues, they are not very open, they are not open to the other part of the world. I don't know what the reason. I should not make such kind of big comment. But they are doing experiment and they are getting the similar effect, and our group has done the modeling, MSD modeling for those laboratory experiments. And you see, it's very simple. Current carrying wires, 4 current carrying wires, they are having currents, they are generating the spatial distribution of magnetic field by Biot-Savart law. And you know, the magnetic field, the middle of the numerical domain, simulation domain is basically the null region, magnetic null of those vessels they achieve, and then little perturbation by a wave. And once we are perturbing it, what we are going to see here, the similar kind of behavior, what we have seen in the sun's atmosphere, what we have seen in the various observations in the Soviet atmosphere, what those Russian colleagues they have seen in their experiment, and so on. So you see, temperature is rising, experiment, numerical experiment is telling the similar physics what is done before. This is a symbiotic relation, and symbiosis is there. I already spoke all those things, not a problem. So, what we are trying to do these days, I am trying to convince various eminent scientists at the globe, and then we have organized a session at Postcard in August in Italy, Florence. And you can see the list. Many established people are coming there who are working on waves and reconnection. So I propose to let's have a brainstorm. Let's find out this symbiotic process, because that is very important. The reason is that still the community is subdivided in 2 parts if we talk about waves and reconnection, and there is little collaboration on such things. So we are going to see, we are going to critically analyze it, and hopefully we are going to establish this concept in over the more wider span. If anybody is interested, you please come there. You are most welcome. Thank you very much. Yes, questions and comments?
Thank you very much for very informative and very exciting talk, Professor Srivastava. Now it is open for open session to audience. If any question, queries, may say.
शिवम वहाँ से माइक ला के देना उनको, वहाँ से माइक ला।
These are the plasma processes which
Sir.
happen in minutes, tens of minutes, or it can go up to, let's say, several tens of minutes. But it cannot go beyond. These are shorter scale processes. Yes. Every observation is complemented by the numerical. So we are doing it within our software. Actually, it is not the software. There are MSD codes like AMR BAC, Pluto, and so on, but they are not having the realistic solar atmosphere in that sense. What we are trying to do. So we are making our own model, and we are just making it embedded in the code, MSD code. It's a bigger structure, but we are making our own model. Because we need those things to understand.
शिवम माइक
No, thank you very much. No turbulence, but of course, we have one research study where we have generated orphan wave packets through this interaction. And our next job is to implement some kind of turbulent conditions to dissipate them. We'll do. So we can discuss.
First of all, this lecture was so nice and it was eye-opening for me because I wasn't aware about this science so much before because I am from biology background. But Manikam Samis, as we are talking about here and we are knowing, India government is spending a lot of money on Aditya L1 mission. And what kind of key findings we are expecting from that mission? And is it really beneficial for common man also? You can explain it. How it would be beneficial for the society as well?
Okay. It's a very important question. Aditya L1 is purely indigenous. So most of the instruments are instruments are basically generated are manufactured from the various Indian institutions. So there is a kind of technical understanding that we do, and that will be used further on, for other solar missions. Okay, and technical advancement will lead this kind of direct knowledge dissemination as well as some indirect dissemination. Likewise, there are many space tech companies are coming out in Hyderabad, Bangalore, and so on. And now ISRO and other allied institutions, they are trying to collaborate with them also. So, this technology transfer and all these things will be being made. And science-wise, it's, as I told you, it is containing every information, starting from sun to L1 point. So, whole suite of observations. And there are many missions, but nobody did that way. So, India is the one who is getting all these kind of data, and its first phase of science has already started. So, scientific advancement will take place. And of course, some global collaborations will be also. The space weather is one of the primary goals of this mission. And the space weather study is being made, okay, using Aditya L1 observation, the in-situ observations. Okay, and all related things are happening. So I think this is a holistic advancement. And another point is L1 point. So we reached to the L1 point. And this is the second solar mission that reached to the L1 point. The first one was SOHO in 1995 by the European Space Agency. Now we are second. So you see the technological advancement, technology transfer, space weather studies, and so on.
Yes, and you guys are doing a great job in this field.
Thank you very much. Professor Srivastava is a very senior professor in IIT BHO. He has published about 300 papers in the literature journals with H index 37, G index 50, I index about 98. He is a member of NASA project Aditya L1. Thank you for this nice talk. I request Professor Prakash to be here and to honor our
रमन हॉल है उसके बीच में जो वैल्यू है मैं एक बार उस पर सभी से बोल दो लगा दे वो अपना हाँ
Professor Bhanu Prakash from Physical Research Laboratory here in University. Please. Okay. Come on, next. And I request Professor Rakesh Saha in the room again. In the memento. He is our guest of honor. Mr. Kuldeep Kumar from Gajah Solar Private Limited, he will sponsor us. And I request Dr. Manoj Kumar to honor Shri Vinipad Bhati from Krishna Automobile is here. I request him to come here. Dr. Anil Govinda, please come on the desk and to honor our sponsor. Again, I request Dr. Ajay Kumar, who is from DRDO. Dr. Ajay Kumar from DRDO. Please come on and give some insights of the DRDO requirement.
Our chief guest, Dr. Darren Sundawar, and Professor and Principal, Shakil Murthy, and background series Abhinav, and distinguished faculty, members, eminent research, scholars, students, and esteemed guests. Good afternoon. It's a matter of great privilege and honor for me to be present here today as a guest of honor at this National Conference on Science, Technology and Interdisciplinary Research. I sincerely thank the organizing committee for this invitation. The theme of this conference is highly relevant in today's era. Science in the 21st century is no longer confined to isolated discipline. The most significant breakthroughs are happening at the intersection of subjects. Interdisciplinary research is not merely collaboration, it is the integration of knowledge, method, and perspective to solve complex real-world problems. Now, as you know, today's era of the artificial intelligence. Artificial intelligence is an interdisciplinary of the physics, mathematics, computer science, and all subjects. Now, the most recent research area for physics is quantum technology. You heard about the quantum technology? Because you are the core physics student, now the quantum computing is based on there are two types of cryptography. One classical and one quantum cryptography. Classical cryptography, they don't have pure mathematics, and now quantum cryptography, they don't have physics, physics law. You know about that, no cloning theorem. You heard about that? No cloning theorem. तो ये किसी को आप जो है इसे कॉपी नहीं कर सकते हैं. आर्टिकल में जो भी है ये आप पॉइंट में आपने पढ़ा होगा इसमें। Now, artificial intelligence, quantum technology, biotechnology, advanced material, space science, and these domains are interconnected. Progress in and accelerates progress in our research today is done. Research should not remain confined to the laboratory for publication. जो आपकी रिसर्च है वो लेबोरेटरी और पब्लिशिंग से सीमित नहीं रहेगी आपको। आज के टाइम में क्या है कि आपकी जो रिसर्च है it should be converted to technology. Okay? Now, this जो आज की जो रिसर्च है it has been developed technology and innovation. Now we will talk technology of technology growth in day-to-day era. Now, the impact of the technology in our society life and physical application. Now, I would especially like to understand researchers and students. Again, here research begins with the curiosity. What is curiosity? Curiosity, our compass. And curiosity must be our compass. Curiosity and how and why. What is this? So you have ability to ask the questions. ये कैसे होता है, क्यों होता है, ये आपके अंदर होना चाहिए। Because you are researcher. Next is एक rigor. Rigor must be our discipline. जो हमारा कठिन वर्क है, हार्ड वर्क है, हमारा डिसिप्लिन होना चाहिए। और प्रथम क्या जो आज के टाइम में मैं आपको बताना चाहता हूँ कि जब हम रिसर्च करते हैं तो हम काफी चीजें लिटरेचर करते हैं तो हमें जो प्रॉपर साइटेशन उनको देना चाहिए। अभी आपने जैसे कि एक शर्मनाक घटना कहूँगा मैं इसको बेलकोटिया यूनिवर्सिटी वाले की है कि किसी का आइटम लेके आपने उसको अपना बताना, ये बड़ी शर्मनाक चीज होती है। तो एक जो मेन चीज याद रखिए आप जो है इंटीग्रिटी मस्ट बी अवर आइडेंटिटी। तो तीन पिलर हैं जिसके इनका हमेशा रखिए क्यूरियोसिटी, रिगर एंड इंटीग्रिटी, सीआई एंड सीडीआई। यानी आपका कंपास, डिसिप्लिन एंड आइडेंटिटी, ये पे जरूर डिपेंड करती है। तो मेरा जो ये नाउ टेक्नोलॉजी बिकम पावरफुल रेस्पॉन्सिबिलिटी become greater integrity and ethics must remain the foundation of the scientific advancement. Now, and I complete the original committee for bringing together scholars and diverse disciplines from platform. ये जो आपका जो कॉन्फ्रेंस है इस सभी स्टूडेंट को एक साथ लेकर आइए, इसलिए मैं आपको देता हूँ। Now, और मैं आपको जो है इस करता हूँ जो आपका जो आपकी कॉन्फ्रेंस चलेगी इसलिए आप सब सीख रहे हैं और सीखें, अच्छा सीखें। लेकिन जो मैं इतनी बात मुझे ध्यान रखना चल रहा है, मैं और एक चीज बताना चाहता हूँ आपको। अभी परसों में अपने छोटे बेटे को जो है थोड़ा सी मस्ती करा दो चाहते हैं, ये 7th क्लास मैंने उसको ये कहा कि बेटा मैं उसको कंपेयर करा दूँ उसको कि बेटा देखो ये वो आपसे अच्छा पढ़ता है, नंबर अच्छे हैं। तो मेरे बेटे ने एक बात नहीं पूछता है कि हम भी कंपेयर करते हैं अपने बच्चों को, भी करते होंगे। तो उसने एक बहुत अच्छी बात कही कि पापा आप कंपेयर क्यों करते हो, कि मेरा नाम वेदांत है, भाई का नाम अंश है, हम दो भाई हैं, दोनों का नाम क्या अलग है। तो एवरीवन हैज ए यूनिक कैपेबिलिटी। आप में देखिए जब हर सब्जेक्ट की हर कैपेबिलिटी होती है, जब सब एक साथ मिलता है सब कुछ एक सोसाइटी के लिए एक आउटपुट आती है। तो हमें उस चीज पर फोकस करना है मेन कि जो हमारी सोसाइटी के लिए, हमारे देश के लिए, हमारे वर्ल्ड के लिए जो भी लाभकारी हो। डीआरडीओ साइंटिस्ट आप जानते हैं डीआरडीओ पिछले काम करते हैं, आर्म फोर्स के लिए काम करता है। डीआरडीओ काम क्या है, मेन काम क्या है, टेक्नोलॉजी करना। मतलब आर्मी के लिए जो हम मिसाइल बनाते हैं उससे क्या होता है, टेक्नोलॉजी होता है, होता है। हम जो है मिसाइल टैंक जो भी आर्मी के लिए देश सुरक्षा के लिए है हम वो चीज बनाते हैं, डेवलप करते हैं। लेकिन हमारा मेन फोकस ये भी होना चाहिए कि हम अपनी सोसाइटी को कैसे बचा के रखें कि युद्ध कम से कम हो। एक अपने आप जो है एक कम्युनिटी बहुत जरूरी है। तो मेरा ये सबसे रिक्वेस्ट है कि सभी स्टूडेंट सभी प्रोफेसर से जो है कि अपनी जो रिसर्च को इस उधर ले जाएं कि जो सोसाइटी के लिए लाभकारी हो। आज आप सबके हाथ में मोबाइल है। आर्टिफिशियल इंटेलिजेंस की पावर क्या है तो पता ही को जो आर्टिफिशियल इंटेलिजेंस की पावर है इसके पीछे क्या पावर काम आती है? डेटा। डेटा में पावरफुल एआई एक टूल है एल्गोरिथम है। तो आपको अपना डेटा को सुरक्षित कैसे करना है ये आपको सुनिश्चित करना है। क्योंकि आज हम जब कोई ऐप डाउनलोड करते हैं तो हम क्लिक करके जाते हैं, हम ये नहीं सोच रहे कि हमारा डेटा कहाँ जा रहा है। आज के टाइम में हम डेटा भाई कोई सुरक्षित नहीं है, हमारी सब आइडेंटिटी हम सब अपने जो है फिर से बोल देती है। हम किसी मॉल में जाते हैं तो कहते हैं सर राइट योर मोबाइल नंबर, तो सैकड़ों हजार मोबाइल आपका डेटा कलेक्ट करते हैं और कंपनियों को देखते हैं। आज आप देखते हैं चाहे जो किसी भी लैंग्वेज में किसी भी उसमें आप तय कर सकते हो, वो भाषा है उनके पास में वो डेटा से समझ गया। तो आप बी केयरफुल। आज के टाइम में जो एक साइबर फ्रॉड बहुत बढ़ते जा रहे हैं। तो आपसे निवेदन है कि आप किसी भी लिंक पे जो है सीधे आप उसको क्लिक ना करें। सबसे पहले आप कोई भी आपको लिंक कोई भी है उसको आप वेरीफाई कीजिए। जैसे आप अपने रिसर्च में कोई भी रेफरेंस देते हैं तो आप उसको प्रॉपर वेबसाइट से उसको रेफर कीजिए, उसको उसकी वैलिडिटी चेक कीजिए। क्योंकि आज के टाइम में आपको DOI वो भी बहुत सारे सकते हैं क्योंकि आजकल फेक वेबसाइट बहुत सारे हो गई है। आजकल जो AI का जमाना है, आप कुछ जो है किसी भी पिक्चर वगैरह सब आप उससे एस्टिमेट कर सकते हैं। लेकिन आपको जो भी डेटा आपको इस्तेमाल करना है वो फैक्ट के साथ करें, उसकी हिसाब से। और जो भी आप इन दोनों में सीखेंगे, जो भी रिसर्चर हैं, स्कॉलर हैं, साइंटिस्ट हैं, वो अपना कंट्रीब्यूशन देंगे, उसको सुने उनको क्या आउटपुट है और हम जो में कैसे यूज कर सकते हैं, कैसे हम कोलैबोरेट कर सकते हैं, कैसे डील कर सकते हैं और कैसे सोसाइटी दे सकते हैं। और ऐसे हम अपने देश को आगे बढ़ सकते हैं कि देश की सेवा में देश के लिए हम कैसे कार्य कर सकते हैं। आप अपने आप को घर एक पूरी पाएंगे फिर यही विचार से और पूरी सब विचार का काम कर रहा है। जय हिंद, जय भारत।
It's my great privilege to introduce Dr. Bhanu Pratap Singh, a distinguished material scientist and chief scientist at CSIR, National Physics Laboratory, New Delhi. With more than 21 years of research excellence, Dr. Singh is a leading expert in advanced carbon material, including carbon nanotubes, nanocomposites, energy storage devices, and EMI shielding materials. He completed his PhD from IIT Delhi and MTech from IIT Kanpur. His remarkable contributions include over 170 research publications, 7 patents, 2 books, and more than 11,000 citations with H index of 56. He is the proud recipient of prestigious honors such as CSIR Young Scientist Award and the Raman Research Fellowship. A dedicated mentor, he has guided several PhD scholars and continues to inspire young researchers. Please welcome Dr. Bhanu Pratap Singh with a huge round of applause.
Very good introduction. Good afternoon to all. First of all, I would like to thank Dr. Manoj and all whole organizing committee for inviting me to this wonderful conference, Science, Technology and Internet. So I will discuss here all three aspects: science, technology, and all three areas related to interdisciplinary, because I am working in the interdisciplinary. So now the topic is carbon nanotube macrostructures in an textual thermoelectric for waste heat harvesting. These are three important words. One is carbon nanotube, second is macrostructure, and third is flexible thermoelectrics. Thermoelectrics very common. You know, this is working on the principle of Seeger effect. There are two dissimilar wires having two different, both are different temperatures. There are temperature gradient in the two dissimilar wires. Delta V. The delta V will be used for the distributed electricity. That means if you sitting in this room, room temperature is 20 degrees centigrade, or body temperature is 37 degrees centigrade, there is a delta T of 70 degrees centigrade. The delta T is the delta V. The delta V will be utilized for making any kind of power. So this is basically the concept behind the thermoelectrics. You see, thermoelectrics, why it's very old, but now I am talking about the flexible thermoelectrics. Flexible thermoelectric basically for the bearable devices, and there is jacket, some body temperature is something else, outer temperature is something else, so it can be used for the bearable devices. The second part, the carbon nanotube. Generally, you know the carbon is a fantastic material, known for the diamond, graphite, carbon nanotube, graphene. This carbon nanotube when you produce, this is in the form of powder. So powder, there is a lot of problem to handle this powder and to convert into any kind of microstructure, component, device, guideline changing. So that's another thing which is called microstructure. Carbon nanotube converted to the microstructure that is going to utilize for flexible thermoelectrics. So that will be discussed in this talk. You can talk about the energy, the different kinds of energy generally used, thermal power plant, nuclear power plant, automobile, factory, natural gas, waste system. All of these energy, only 34% of energy is used. Rest is just like a waste heat. So that waste heat had to be utilized using the thermoelectric module, converting into the electrical energy. That's the advantage of this thermoelectric that we are going to already this is basically depending upon the Seeger effect. The Seeger effect, there are two different types of semiconductor, P-type and N-type, and the temperature difference, then it generating the electricity. So this is basically depending on several parameters, anode efficiency, figure of merit. So one of the most important part of this thermoelectric is figure of merit. The figure of merit is Z-T. See, if you talk about thermoelectric, it is a very important formula. This is called Z-T equal to S square equal kappa to T. So it is depending upon Seeger coefficient, electrical conductivity, and thermal conductivity. So if you have a higher Z-T value, it should have a high Seeger coefficient and like electrical conductivity, but it should be very low thermal conductivity. Now see this graph. This is a very long history of this thermoelectric starting from 1940s, and then this Z-T value increasing up to further year 2070. Then there was stagnation of this graph up to 1992. So the people start saying that the now Z-T value is not improving, so people started not to work on that. But in 1992, there was a gentleman called Professor Boss. He said that if you develop structure of this material, you can further increase the Z-T value. So this is basically how you can improve the Z-T value accordingly. So that's why we are going to discuss here how this carbon nanotube material is utilized for physical components. Now come to the carbon nanotube. This is the carbon nanotube, most of the people must be knowing, carbon nanotube, single wall carbon nanotube, multi-wall carbon nanotube, double wall carbon nanotube. These are basically produced by either by the, you can say, chemical weapon deposition, laser, and art discharge. These are three most important techniques by which the carbon nanotube are produced. But when we are producing this carbon nanotube, we are producing this powder. the 0.4% of carbon residue to the polymer because there is a large agglomeration of carbon residue, viscosity of the polymer will increase. Simultaneously, what is actually happening? Because generally, instead of very small of carbon residue, you are modifying the property of polymer, not exploiting the property of carbon residue. So the thing is, how to improve the amount of carbon residue to the polymer or any kind of component device, that way you need some kind of network structure. So the network structure are, this is one of the network is called carbon residue paper. Another is called carbon residue sheet. This carbon residue can also be the fiber, yarn, this can be converted into this network structure. You see how this converting network structure from CNT is a bucky paper, carbon fiber sheet, and then there are large number of applications for derivative storage, conversion, sensor, filtration, absorption, structure component to field emission. Now see how this is basically our process by which we synthesize this carbon residue powder. This is called CVD, chemical vapor deposition. And in this chemical vapor deposition, this carbon residue powder is formed, and then we can produce more than 100 grams of carbon residue per batch. Then we have same, and then you can say I have 90, and then you could go 2.2. So these are all parameters of diameter in the range of 50 nanometer of these carbon residue. So this synthesis of this carbon residue by the CVD, this is produce the powder. Now we are going to convert this powder to the sheet or the paper. This is called flexible CNT paper. So first we have the carbon residue. This is the multiple carbon residue. This is put into DI water, and then there is homogenized or very high speed of 20,000 RPM, and then add some kind of surfactant. Then again the mixing of this by the help of sonication, and this suspension is basically vacuum filtered with the help of vacuum filtration unit that can convert into the CNT paper. This is basically size of 35 cm by 35 cm, and then we demonstrated it for different kind of applications. This carbon residue paper, and starting from ballistic protection, anode material, lithium battery, supercapacitor, photo detector, thermoelectrics, lightning kind of resistance, and EMI shielding, and different kind of application which has been published in different papers in the patent form. So now see, here we are able to develop this carbon residue paper of size of 35 cm by 35 cm. Right? So the CSI here is basically for the translational research, for the technology for the industry. So need to scale up this process. So we further scale up this process to the meter scale. The most important part is there is no wind up no polymer. This is carbon residue paper. Only because this powder has been converted to the paper without any wind up of the polymer. See, further applying this carbon residue, we are able to convert it to 1 meter by 1 meter of this carbon residue paper. This is the basically roll of 1 meter by 1 meter of carbon residue paper, and then we license this technology for industry. Then industry goes to commercialize this product with the carbon residue with the carbon residue paper. So this is the basically process of making batch scale. Further we want to take a load of this carbon residue paper. We can also have a process by which we can convert this carbon residue into larger scale roll of carbon residue. This is another process for making the roll a continuous process. You have this is a setup. First you have to prepare the CNT suspension, then pour the CNT suspension into the hopper of this setup, and then this is moved to this kind of block, and then this and with the position of the kind of block, the drying is taking place and the rolling. This is the roll of carbon residue paper more than 2 meters long. So the thing is, this carbon residue powder, now we have a process by which we can convert this into very complete roll. Where we can implement a different kind of application as well. Composite material, ballistic material, thermoelectric, light, lithium battery. So the people are used to say the carbon residue very small in amount, production is very low. It's a basically scalable process with a bigger larger scale, which can have large potential of different kind of applications. Now this is the process by which we are using this carbon residue powder into the paper. Another technique which we generally use for making carbon residue. This is very interesting. You see, this is called FCCVD, floating cation chemical vapor deposition. What actually happening? In this, there is no solvent. What is happening in industry? Get a powder, they mix it with some kind of solvent. Here we have at the time of synthesis, this is converting into the sheet. So what is this? The process containing carbon precursor that is ethanol, there is catalyst called ferrocene, and the product is called thiophene. The mixture all these three injected into the furnace at high temperature, around temperature of 1350 degrees centigrade. So what's happening in the middle of the furnace, the temperature is 1350 degrees centigrade. This carbon residue form just like cotton, that is formed. Then we take it to this form, and then we deposit it on the metal. And this is called the more diameter of 8 to 9 nanometer. Previously, carbon powder was having a diameter of 50 nanometer, in a very low diameter of 8 to 9 nanometer. And then I came on ITC, the around 6. Previously, it was around 2.2. Even highly improved quality of carbon atom, no need of any kind of solvent, you can convert this into the carbon atom. You see how this is coming out? This is a furnace. In the furnace is a metal, and the metal is depositing in situ. So this carbon atom is basically from the center of the furnace, it is stretching out and depositing on the metal. Now we come to the thermoelectric part.
वीडियो की वजह से
So the previous process like it produces carbon atom powder to the paper. Now how we can utilize the thermoelectric application? See, when you have to make any kind of thermoelectric device, you need a P-type component and an N-type. So P-type and N-type. Two carbon atoms is a P-type thermoelectric element. So now we have to convert this P-type to the N-type. So there is some process. The process is called incorporate polyhydramide. This is called PEI. To dope the PEI, the carbon atom is P-type converted to the N-type. So you see a different concentration of material, especially the optimized 9% and 12% of PEI, the converting this carbon atom to P-type into the N-type. You see how this is the P-type and N-type is the CVEC coefficient. CVEC coefficient of a carbon atom paper is around 13. 13 microvolt per gram for the P-type. Then we drop acetate with the PI solution, converting this P-type into the N-type. So confirming this is the P-type or N-type, we have to again measure it. To see the XPS spectra, XPS spectra says N, the peak of nitrogen. We are adding PI, the polyhydramide, the contribution of N, showing the XPS. This is the doping has been taking place on the on the carbon atom paper. So now this is thermoelectric performance. The top part is basically whatever data on the P-type thermoelectric material. This is a CVEC coefficient around 13 at room temperature, and then it is 9. So at this value is N-type is negative. So the CVEC coefficient of P-type material is the positive, and N-type material is the negative. So now you see after doping, you have both P-type as well as N-type material. Now see now you need to get some kind of device. When you do the thermoelectric, now you have P-type and N-type. See, we taken 3 pair of P-type and N-type. See, this is the black one is the P-type and another one is the N-type. You see the P-type and N-type, one P, one N, one P, one N, and then the power connection has been taken to get contact. After that, these are temperature hot and cold side. So they are delta T of 10, 20, 30 and 40. When they are delta T of 40 temperature, you see the voltage has been generated. Voltage is around 5 to 6 millivolts. And then we measure the power. You see the power is coming around 5.5 nanowatt. You see this 3 pair of P-type and 3 pair of N-type generating power of 5.5 nanowatt. So you see the 5.5 nanowatt of the nanowatt power we use with the thing. No way you are going to use the power of the nanowatt. Okay. You see. So now what we do? We have only 3 pair of P-type. Power is only 5.5 nanowatt. Where are you going to use this 5.5 nanowatt power? So, increase the power, you need number of layers to increase. So, what we did is carbon atom paper was flexible. We have perfect sheet, and on the perfect sheet, we binded this carbon atom paper in such a way. See this? This carbon atom paper is binded on the perfect sheet. And these are basically 60 number of layers. The front side, and then back side we have brought up the PI solution. So one side is the P-type, back side is the N-type. So now we have P-type and N-type. There is continuous leakage. There is no need of making any kind of connection. Why there is no need of making connection? Because carbon atom system is highly conductive. So no need to make any kind of contact connection. So this is more power is the maximum holy volt. But we also demonstrated, you see this device was kept on our hand. Because the body temperature is higher and outside temperature is lower. This is definitely around 2.3 Kelvin. It's showing some kind of a voltage generation. Then we also put it in the example of the bike. Where vector is slightly higher. Because 39.5 and lots of cases slightly lower than more than 50 degrees centigrade. Then we get more power. And then the put the example of AC. And then the another kind of device, this is called LIGO type of device. Inside part is basically hot and put in a finger, outside is a door. So that also generating some kind of power, there is move somewhere, the touch is clear, all these kind of activities. So now, still, what we have done, we are able to take some kind of device, the P type or N type, but output power is very low. So what is the process by which we can increase the output power and the voltage until unless they are not going to increase this power, they are not going to utilize this kind of device. So, need to larger signal coefficient and power factor. So one thing. See, here, as I in the beginning of the orientation electrons or all this is not a new thing. It's a very old. Inorganic materials are used from several years. But the problem is with inorganic material, the problem is high rigidity, expensive toxicity, and a complex process is most important. This is inorganic material written in nature and the complex possibility. But it's high thermoelectric performance. So if the organic thermoelectric is flexible, expensive, low toxicity, high weight, but low thermoelectric performance. So see, it has to consider the flexible, another side is better. So if you hybrid organic thermoelectric material can solve the problem. So zero coefficient of power factor is the problem of the inorganic thermoelectric material and the flexibility and processability will come in the carbon level. So the idea is to utilize both carbon and these two important thermoelectric materials called BiEC and KgFbU for low temperature region and high temperature or medium temperature activity. So this actually integrated these two inorganic thermoelectric materials with the carbon atom to make hybrid flexible thermoelectric device to improve the signal coefficient and the thermoelectric performance. See, to say it's very easy to integrate organic and inorganic material. Two different type of things. Matching the inorganic or very complex. The low type parametric low is very mushkil. Similar type of thing, organic and inorganic combination phenomenon integration is very challenging. So we tried around last 2-3 years to make good integration that improve the performance. See, first thing is as you use carbon atom, there is no functionality on that. Not to modify the surface of this carbon atom to see by using a function by utilizing some kind of function. The second part, can the BiEC is an anti-thermoelectric material and AgFbT is the pre-thermoelectric material. So in the solvent, this is called twin ionic, behind ionic, BiEC power on this, and then the seed one basically the compressed seed one built on that. This is basically for the BiEC will go or PCFBC. This is called BCND. Then another part is basically AgFbT is a segregation of different kind of solvent, which is called NMP solution, and then this process later was dipped into that. This is showing AgFbT to powder and NMP and showing ACND. So now we have ACND is the p-type thermoelectric material and BCND is the n-type thermoelectric material. See, this is the other kind of all kind of analysis. Then when we talk about Raman analysis, in the carbon atom contains G-band and D-band. And multiple carbon atoms does not have any kind of a low wave number. See the low wave number is AgFbT having a 2 important peak at 129 and 255, which is showing in this low the AgFbT is very C. Similarly, when we talk about n-type thermoelectric material, the incorporation of BiEC, similarly this P in this has been seen showing this integration of this carbon atom has been taken. How this integration has been made, you need to show because of current exchange analysis. What kind of bonding agency? See the crystalline carbon atom, when it is punctured, there is very small thing of gold. It is a very important thing of gold agency. So this is carbon atom has been punctured. So new overpeak appeared in the accelerated control successful puncturization. Now come to this, how the integration of this inorganic material has taken place with the carbon atom. See, to not come to the details of chemistry. So see, this is basically the mechanism by which this has been, you can say that this is a complex carbon atom, then this is a different ion, and then is helping with the BA-53, and then it's going the BA-53 with the help of BA-53 is a basically coating on the carbon nanotube surface of that to the core, and then it was basically amylase. It's helping control with the help of metal carbon bonding after the 400 degree centigrade and metal nitrogen bonding. So some kind of a bonding between this carbon nanotube is seen with the BA-53 in order to electrometry. Secondly, the ACNT is basically the p-type thermoelectrometry ADLPDU. That case is acid basic reaction taking place. The name of the NMP that making the integration of this ADLPDU is the carbon atom. So this is basically not the possibility of the reaction. So now you have seen the integration of ADLPDU and the BI-2 is the carbon atom. This is the sometimes and the display. Now come to this is the important part. Previously, the senior coefficient of this carbon atom paper was 1230. This CNT coefficient of the senior coefficient is 38. When we integrated it, the p-type of AgSNT2 is 57, and then the n times of 58. So the C previously it was plus 12 plus 13, now we have 57 minus 58. So this senior coefficient much higher as a previously carbon atom based material. Then we take this 3PA device. Now see the 3PA device. Previously the voltage was 5 to 6 millivolt. Here the voltage is up to 24 millivolt. Can be higher, but this is the voltage. This is like much better. And then we see the output power. For 3PA device, this output power is close to 2000 nanowatt. If I only 5 to 6 nanowatt, here is 2000 nanowatt. So measure higher than those. And see the power, but this is only 3PA device. Then we further increase the number of racks. This is basically the 40 PLPA. 40 PLPA, we just 3PA. 40 PLPA having the VOC of more than 300 millivolt, and this power is 50 microwatt. Now see, from the 500 nanowatt to 50 microwatt, this is 100 times higher than this power. So that means if you put the performance of comparative material in this carbon nanotube, the property of this. So microwatt power can be utilized somewhere in the generator devices, the charging or this bars and smart bars. This can be further utilized in other applications. Then another one, that I am not going to much of detail. Madam saying time is over, so but I will just try to conclude it. Basically, there are two different materials, AgSNT and BI-2. This is basically used at low temperature. The another material is called the heat-based heat, different kind of heat. At the body temperature is low, there is a low temperature, but sometimes there is heat which is 200 or 300 degrees centigrade. And that 200 or 300 degrees centigrade need a material that can burn at that temperature. So CuSN3 is another material that can be applied for the temperature of 200 or 250 degrees centigrade. So we have integrated CuSN3 with this kind of carbon nanotube, and then we see the thermoelectric performance. So we are just coming finally on this. You see, this is plus 81 and minus 73 up to the position and become the CuSN3, and then this is a 3PA device. It's again so a similar kind of a voltage instead of 20 millivolt and power 43 microwatt. And then we also created this device, the 39 pair of device, which is also showing close to 50 microwatt. And then this is our design family. This control is red, and these are utilized this carbon and this control particularly the LCC device carbon seed, the potential crystal convertibility. For further improving performance of carbon seed, hybridization of CNT is the high performance erosion convertibility like AgSNT to BI-2, CuSN3 performance tools. These materials to the great potential for the application of the crystal convertibility. Now, I can knowledge. और ममता मनोज लक्ष्मी का लक्ष्मी transfer the curriculum and electoral committee and proposal we will have design application of the Minister from GNC that is electoral committee accepted we are going to thank you sir. Now any question please. Yes sir.
चाबी आपको दे तो दी थी सर, तब मैंने कहा तो था मैं नहीं रखूंगा, आप रखो अपनी जिम्मेदारी, मैंने तभी आपको पकड़ा दी थी।
How does this compare with
नहीं सर, मेरी जेब में ही रह गई।
the CMD papers and Kevlar? How does it compare in terms of cost? Both are ballistic.
Yes. You see the ballistic material, either it is in Kerala or there is another material is called Spectra. We have two materials are used in the ballistic application. Kevlar and Spectra, they are very good material, but the problem is the density. You see, the Kevlar has a density more than 2. This carbon-native paper density is less than 0.2 gram per cc. So when making any kind of ballistic material, the challenge is how to reduce the weight. So another technically, one important parameter is required in the ballistic material, the impact resistance and straight to failure requirement. How much elongation can be taken place with the when the bullet is impacting onto the surface. So the carbon nature of the material is having elongation to break more than 10 to 30%, which is around 3 to 4 times higher than the camera.
So cost-wise, this is cheaper.
Yeah, cost-wise is still there is a challenge. Lot of work is still going on to reduce the cost. If you compare the cost, the camera is higher.
Sir, actually I am working on a home protection technology. I make a device. Here's the device. Can I?
Yes, come please.
हमारे यहाँ से देखो कोई भी नहीं है।
करंट देंगे तो वो टेम्परेचर डिफरेंस होगा, टेम्परेचर कूलिंग के लिए यूज करता है। दिस इज पावर जनरेशन अनदर वे इज द कूलिंग फॉर
Very informative. One question, my question. कि सेम पेपर के प्लाट के बाकी पेपर what are the same things here that
I showed different kind of paper here, but whether it is CNT powder is converting into the some kind of CNT suspension that will filter into the paper. This is also same thing with the buggy paper we are talking about. The same thing, only the scaling up. The second process, which is called FCCPD, this is not the buggy paper. This is basically called CNT seed. CNT seed, difference in the both of the case, in case of the buggy paper, the carbon atom randomly oriented. example, that case of accessibility, these are partially aligned. Because this is the 80% or 70% alignment of the army to take place in that. This is a big difference. Okay, thank you. Sir, yeah.
Thank you, sir. Nice presentation.
तो बेटा को बेटा ले
Myself, Sandeep. Sir, my question is that what about the brittleness of the sheet?
Sheet is very flexible, is not very flexible.
Yeah. I think the thickness of the sheet will also affect this thermoelectric effects.
Absolutely.
So I think there is some some adjustment between the thickness and the properties of these sheets.
Yes, thickness affect both thermoelectric performance as well as flexibility. If you make a very thick sheet, then flexibility will be reduced. So the thinner the sheet, more the flexibility. Similarly, when you talk about thermoelectric performance, you cannot go beyond certain level of thickness. Then when the charged areas are there, how it is low, you need an amount of carbon landing also there. So this is a case sheet about 20 micrometers, the second case. We optimize 20-25 micrometer of sheet is sufficient for such kind of devices.
Thank you, sir.
Thank you, sir, for the incredible presentation and the knowledge drops. Now I request Dr. Manoj Kumar to felicitate Dr. Bhanuprata by giving him a token of remembrance in the form of a memento. It's an honor to introduce Professor Anil Kumar Ravi, former head and professor in the Department of Physics at CCS University, Kerala. With over 25 years of academic experience, Professor Malik has made significant contribution into tetrahertz politics, laser plasma interactions, metamaterials, and quantum optics. He has also served internationally at the University of Stuttgart, Germany, and the University of Oxford, Brazil. He has published more than 100 research papers, holds patents, and has guided many doctoral scholars. His global fellowships, including TWAG and double fellowships, reflect the academic excellence. We are truly privileged to have him with us. So, the stage is all yours.
So, good afternoon to all. The journey started from nanotechnology to suddenly jumped into solar physics, then to carbon guy, and now you have here photonics, right? So multidisciplinary is really difficult to handle, and especially when you are listen multidisciplinary topics, and always difficult to. So I am really thankful to the organizers for having so wonderful esteemed speakers here, like Srivastav from BHU, A.K. Sarma, Professor Vats, and Bhanu Pratap Singh, my friend, and some even more guys, eminent guys here. I'm thankful to inviting me here within this platform to interact with the young minds. All the most of young minds are back because of lunch, because hearing lecture before lunch is always difficult. People are supposed to be hungry. And I have been told that I have to finish it in within 25 minutes, also difficult job. So here I have to talk about new class of materials. That is what we call metamaterials. I don't know how many of you have heard about such materials. Can you raise your hands? How many of you have heard about such materials? Okay, good. Two guys. So metamaterials are a special class of artificial materials. They have supernatural properties. They are man-made. They can be manipulated at your will. That is the beauty of these materials. It's a very versatile platform. Metamaterial is a versatile platform to manipulate electromagnetic waves throughout the spectrum and an extreme scalability. Means in this case you have everything in your hand. Everything depends on the same size and geometry of the materials. If you see conventional materials, most of the people who work in these kind of materials, here you see permittivity and permeability, both are intrinsic properties of the material. They are positive. So most of the conventional materials bear positive refractive index. If you jump into the plasma, your refractive index becomes between 0 and 1. In conventional materials like solid gases or liquids, your refractive index comes out to be 1 or greater than 1. But here I am talking about the materials whose permittivity and permeability both are negative, and as a result your refractive index is also negative. So I am going to talk here about the negative, double negative refractive index materials. Although these kind of materials never occur in nature. So you come across this Snell's law. What happens in Snell's law, if your material is positive refractive index material, your K vector and energy flow, you see this is K vector, this shows the direction of propagation of wave, this direction of wave velocity, and this is pointing vector which is basically carrying energy with the wave. So here in this case, this is basically positive refractive index materials where energy flow and wave direction are same. But in 1968, Victor Vassallo proposed different kind of materials. He was basically a German physicist, and he basically predicted the possibility of opposite properties for artificial materials. Means whatever conventional materials have, these properties are totally different, opposite properties. After 1968, there was a vacuum for 35 or for 30 or 31 years. Such materials were not realized at all. And John Bentley in 1999, first time theoretically proposed that such kind of materials can be fabricated, can be synthesized or can be fabricated. And after 2 years, just after 2 years, these such materials were fabricated. They were realized at all. And such materials as reverse thermoradiation, reverse Doppler and opposite phase group velocity. That is beauty of these materials. How he comes to just give such calculations, he basically started taking this free space diagram Cartesian coordinate grids, and he find out that in if you sine an electromagnetic wave, it travels in a straight line. Then he tried to just distort the geometry, Cartesian geometry, and he found that along with the distortion of Cartesian geometry, your wave propagation will also distort. That was the basic idea behind developing such materials. You see, in such materials, your wave propagation, the wave vector is propagating in this direction, this is direction of propagation of wave, and your energy is flowing in the opposite direction, completely opposite direction. This is a kind of miracle. How mathematically this come up? Then is define your refractive index by square root of relative permittivity and relative permeability. Then if you incorporate phase in that, then definitely you multiply this and will come up with a negative factor. I am not talking about the value exactly, but the value of this refractive index. My basic aim here is to just show how this negative sign of refractive index comes into picture. Although negative permittivity and negative permeability occurs in nature, but not simultaneously. There are materials where you can see negative permeability, you can see negative permeability. For example, silver, gold, and aluminum, there is negative permittivity for certain frequencies. Similarly, resonant parametric systems also display a negative permeability at resonance frequencies, but simultaneously there is no natural material which can show both negative permeability and permittivity at all. Can you see how this? Yes.
Next.
Yes, you can see the wave is incidentally, this is mathematical. You say this wave is incidentally on this mathematical. And you see, this is the direction of propagation of wave velocity, and then energy is moving the opposite. This is both wonderful property of such kind of materials. Here, wave is incident this way, propagating in this direction. This is the direction of phase velocity, and this is the direction of move velocity. Yes. And question comes: how can we arise for artificial materials to get negative permeability or negative permeability? Here you see, can we propose that if we prepare artificial lattices with the help of some metallic rods like this, then by using root model, if we make this factor is greater than 1, then definitely permittivity will come out to be negative. So what he basically suggested, he create an artificial lattice, the lattice parameters, and using this just manipulating this plasma frequency with the help of lattice parameters, as he calculated like this, where light C is velocity of light, S is lattice constant, and A is basically radius of this rod or diameter. So we find out that plasma frequency can be manipulated with the help of these lattice parameters. And if you see, we plot this permittivity like this, that this graph will comes out with this. If we fix this omega p here, then all the frequencies omega or radiations below this frequency, this material will act like a negative permittivity material at all. So by changing this, by changing lattice parameters, you can fix omega p, you can shift it to the right direction, and you can shift it that direction. You can manipulate that by just manipulating these artificial parameters, these lattice parameters. You can fix that, and this particular material will act like a negative permittivity material for all radiations below this omega p frequency. So that is how you can just make negative permittivity materials. Then we just look for how can we artificially develop negative permeability materials. Then you know that this is bulk material like this, and you will not see any, if you go interact with this, you will not see any magnetic dipole at all. If you make it a ring, then definitely electron will go on the surface of this ring, and it will act like a magnetic. So magnetic field will come into picture. Then if you cut it, then it will act like a RC circuit, because this cut will act like a capacitance and the circle will act like a square. This will provide you inductance signal. Then we try to make double rings, or double split rings, then definitely a magnetic field will enhance. And by that way, by making another lattice by using such rings, he just proved that permeability can also be negative in that way. The question comes because our basic aim is to get negative permittivity and negative permeability simultaneously. And what we propose that can we combine these two structures together? If we combine these two structures together, then this structure is basically responsible for negative permeability. But apart from that, we also find that if you sign an electric field, electromagnetic field, if your horizon of electromagnetic field is along the rods, then it will behave like a negative permittivity here. And if you sign your electric field, if horizon of that electric field is perpendicular to that material, then these materials act like a directly company. They will not act like a negative permittivity here. Then they will combine them and they find it out that double negative materials to obtain double negative materials are possible. So these are the structures initially proposed. So as a summary, you can see that metamaterials are nothing. It is an array of structures available elements. Simply as in conventional materials, you see the lattice structure. Here we create artificial lattice structures with the help of rods and wings. The precise size, shape, and geometry, orientation, and arrangements are the important parameters. Means whatever property metamaterials obtain, it doesn't depend on the material property, intrinsic properties of the material. It majorly depends on the geometrical parameter. So metamaterials allow for explicit design of effective parameters like permittivity and permeability. These two parameters are you can manipulate them as per your requirement. Most salient the future of such materials are their metamaterials draw their properties from the geometry, not from the chemistry or band structure. What happened in case of conventional material? The market is growing very fast. You see, it is growing CAGR 36.7%, huge CAGR. And we are accepting, if you see the contribution, the reason why North America, United States of America is a leading player in this area, then Europe, then Asia Pacific, and the Middle East, and Africa, and South America. So the major leading part is basically taken over by North America. These are basic companies which are working in this area, and these are basic segments, areas where metamaterials are being used. You can see that metamaterials are in healthcare, telecommunication, aerospace and defense, electronics, energy, power, and optics. So my basic concern here is about optical properties of metamaterials. You can see here in 2022, the market of metamaterials was only $0.9 billion, and it is expected that it will and it is expected that it will be $14.5 billion by 2032. That means in 10 years span, the market will expand from 0.9 for almost 15%. That is all. Now, because I will discuss about terahertz metamaterial, so I like to discuss about terahertz. Terahertz is nothing; it is a very tiny frequency band on the electromagnetic spectrum. You can see here, with 0.5, 0.1 terahertz to 10 terahertz, almost very tiny. It is being covered. It is sandwiched area from electronics and photonic side, and that is why over the explored for a long time. You see, it is 30 micrometers, correct figure, and its photon energy is around 4 million electron volt. That is, you can see the most of the bulb. 75% emission from the bulbs are metamaterials, basically terahertz. So I will just club these terahertz with metamaterials. The applications of these metamaterials are in different areas. You can see super lenses, blocking, sensing, absorption, and slow light lenses. I will discuss more about two applications of that. So super lenses consist of metamaterials to achieve resolution beyond diffraction limit. So with the help of metamaterials, you can developed, people have developed super lenses whose resolution is much higher than the conventional lenses. And you can see that with the help of mathematical super lenses, even you can detect viruses directly, or you can just observe the DNA structure. So that is power of this. Probably people have come across these two movies. Most of you. Harry Potter, how Harry Potter hides himself. This is not the help of mathematics, because at that time mathematics was not there. And you have also, probably have also watched this Mr. India movie. Right? So this mathematics can do this magic also. Because it is possible with the help of mathematics that you can bend the light, bend the propagation of light. You put mathematics here, you put anything inside that activity, it will be invisible. You cannot see that material if it is put inside this material. I will show you here one example. Put apple inside that cavity, it is not visible. Here you can see if you put mathematics in that particular segment, it will not be, that part will not be visible at all. So this is a very good material for speed technology, and that is why USC is very keen to develop such materials in a very fast way. Mathematical seed height. Yes. That the road is you can see this road. On this side, road is mathematical seed. Can you see? You put metamaterials sheet, the guy is becoming invisible. You can see the background, but you cannot see this guy. So this particular phenomena is known as optical clocking. So this is the main reason why America is pretty much interested in developing such materials, useful especially for defense technology. But the problem with this technology is, if you cannot see that guy cannot see.
हमारे टाइम में भूत यही यूज करते थे लग रहा है हमारे भूत यही
तब तक नहीं था. First accelerator demonstration था at around 2001. Yes. So let us come to the sensing part, because that is my topic. There are so many ways to use this metamaterial for the sensing purpose. You can use as a thermal sensor, you can use this material as a acoustic sensor, you can use them as a mechanical sensor, and you can also use these materials as an optical sensor. So my basic area where I am working is optical sensing. In case of optical sensing, these four parameters are very important, and we are going to this particular area. First parameter is sensitivity, how sensitive a material is, the sensor is, and then selectivity, and then quality factor, and the last factor is figure of merit. So these four take care of when you are doing this. So this is our first result. I am going to say how much. So this is our first sensor. First result, we basically design a decagon structure. We develop a lattice here, and then we find it out in such this is each here, because I have been told 5 minutes, I have to within 5 minutes. So here you can see
फिर अजय
These are basically results in here.
फिर ऐसा शेड्यूल क्या है क्या नहीं
What basically we put cancerous cells on this particular structure, this particular seed, then what happens to that, its environment will change. Means effective permeability will change. When you apply something on it, when you change the environment, definitely refractive index will change. And our sensor or metamaterial will basically sense how much change in the refractive index. Because once refractive index change, the resonance will shift, and we observe this resonance like this. And you see, by applying cancer cells over here, we observe that 108 terahertz was there at frequency of 705 terahertz. So this is huge signal. This is very sensitive device in that case. These are power factors, these are quality factors. We don't manage at all. Our quality factor was coming out to this 700, and this is huge, very high quality factor and very high sensitivity. So what we can also try to model that, we use transmission line theory, and we just convert, as I already told you, that your structures, resonant structures will work like an RC circuit. So we try to make this model on the basis of that. We calculate capacitances, we calculate inductances, and just try to find out circuit impedance at all. And then total impedance, and skipping this mathematics, how we calculate inductance, capacitance, and resistances, and then just check with the data, transmission data in these results. And we found that our model and simulation results are good agreement at all. So we first time propose this mathematical model how these materials can be designed. Yes, this is sensing for cancer cells. This is for healthy cell, and then if we apply cancer cell, then this particular cell. These are the coupling of interactions. You can see the practical magnetic field here. Another example, very good example is absorber. Because steel technology is not based on optical clocking. If suppose we send some signal of a particular frequency, if the device absorb all the signals, then it will not return any signal to the radar system. Then absorption technique can also be used as a steel technology. So we also try to that. So this absorption method can also be used for sensing purpose, for steel technology, and for certain other purposes also. You can design antennas, you can design radars, absorbing material. If you break your metamaterials on the radar system, then it can be invisible to others. Microwave sensors can also do something like that. So we also try to basically fabricate absorber using terahertz, using metamaterials. So we just try to make a good type of structure in that. Here you see where we just put it. We just put a metal bottom sheet, and then the metal sheet, and then we put directly sheet over here. And we signed around radiations to that, and we found that there was no transmission, no reflection at all. And we just observe the number of this particular model I am explaining. We find out so many resonance peaks here. So this particular device can be used for multiple wavelength sensing. It can be used as a broadband absorber. These results in scientific. We just try to sense air, fungi, and yeast by using that sensor, and we find out how this is basically air, and you see this is fungi. There is a significant shift in the peak, and you see this is yeast. So a significant shift you can see here also. These are interaction lines. Then these devices can also be used to track a photon, to slow down the photon, and we also develop that structure by using these aligned structures. And we find it out quick transparency windows LED fact here. 1, 2, 3, 4, 5, 6. Because even today there is a challenge that we can fabricate an absorber for a very small band of the frequency band,
But challenge is that can we just expand it to a broadband structure? So this is way you can see we have a very large band from 0.5 terahertz to 5.5 terahertz. We are able to develop that. And another beauty of this, you can just clean the bands. Means you can clean one peak with the help of increasing parameters. Separately, you can also do twin, second peak, you can third peak, fourth peak, and fifth peak separately. And it is also possible to manipulate all the bands simultaneously. Means by just changing the parameters, you can do one peak at a time or keeping other peaks as such, or you can also do all the peaks simultaneously. That is also possible in this. And we find out that we were able to track your proton for 6 picoseconds in that case. This model we developed, the line model, extended transmission line model. We basically developed this model for n such circles, for n bands. That means it is also possible to expand it further to the area of 5.5 terahertz. So that's all. Metamaterials are important artificial materials at definition. Due to strong resonance interactions, metamaterials have enormous applications in optical clocking, observers, superlenses, photon trapping, and sensing. Metamaterials research and market has expanded very fast. That's all. So I just skip all that. Yes.
Can we do the reverse? Instead of decreasing n, can we increase n?
N?
Yeah, the refractive index.
In which negative direction?
Not to go for the negative direction.
Take the mathematics it is not.
It's not possible.
Because basic purpose of metamaterials are to enhance the interaction. Interaction with the material. This is an intermediate device. If you want to, because you see most of your characterization techniques are based either on electron dynamics or on photon dynamics. So what you want to do, you want to have an intermediate device so that you can enhance interaction with the material. If you want to study some material, then you want to enhance the interaction. So here in case of metamaterial, that is possible.
Sir, just like this photon trapping is very important because it gets slower down.
Yes, yes.
It can be transported to nuclear reactors. The size of the nuclear reactor will be reduced to very small.
Yes, obviously. If somehow we are able to develop commercial metamaterial, then definitely it is good for nuclear reactors also. This technique is good for solar panels also. The developers are good for solar panels because if you put a metamaterial sheet over solar panel, then because you see light, we were able to find out. Yes. Here you see the absorption coefficient is almost half. So it is possible. This is the absorption coefficient is coming out to 9.9 almost. So in that case, definitely it will have to enhance the absorption for solar cells. People are not using that technique.
जो most efficient solar cells है वो कि 0.4 तक पहुँचता है.
यहाँ पर absorption अगर आप लेयर एक लगा देते हैं
वो नहीं कह रहा है.
तो that absorption dependence and definitely efficiency of solar cell can be much higher than whatever we are getting right now. We are developing a small segment for DRDO. Here we are just making a metamaterial liver just for sensing of some bacteria and all. We are trying to develop that. With the collaboration of other IIT Open, we recently received a project. So lot increase basically different technology in today, not to do that area. But definitely once it materialize or commercialize, things will be different way. Any other question?
Thank you, sir, for the insightful lecture. Physics this morning. It's my pleasure to introduce Dr. Suman, Assistant Professor in the Department of Zoology at the College of Gurgaon. She has completed her PhD in Neurophysiology from AIIMS, New Delhi. Her expertise includes neurophysiology, electrophysiology, transcranial magnetic stimulation therapy, and molecular techniques such as PCR and ELISA. She has published many research papers in reputed journals and is an active member in several national and international scientific societies. Let's welcome Dr. Suman with a huge round of applause. I know mostly people are taking their roaches for lunch. I assure you I will wind up in 10-15 minutes. Many congratulations to the principal sir and the organizing team for conducting this national conference on science, technology and interdisciplinary research. And thank you for giving me the chance to present here. Before start my topic, I just want to say physics is the soul of all sciences because it provides the fundamental laws that govern the matter, space, energy, and time, and that underpins zoology, botany, and chemistry. In fact, all the sciences are deeply interconnected. Without physics, many chemical, physical, and biological processes cannot be fully understood. And the chemistry forms the bridge between the physics and biology. And also the biology uses the applications of chemical and physical principles. So yeah, since morning we are reading the physics. Let's have a quick glance on the biology, a brief history of that. So the first eras began with the Aristotle, where they classified the living organisms, and till 18th century mostly theories were given like Lamarckism and most famous the Charles Darwin theory of the natural selection. I hope all the people have heard about this. In this mostly theoretical part was done. Now, yeah, at this time the physics became more to the biological sciences with the discovery of this compound microscope. So with that, when the first cell was discovered, and later with the other microscope like scanning, electron microscope, and these sciences like cell biology, cytology, and the basics of genetic they have emerged. I hope all the physics people have heard about DNA also. Yes. So she was the lady Rosalind Franklin. She again used the physics technique, that is X-ray crystallography, to define the structure of the 3D image of the DNA. And later these Watson and Crick given the basic of the 3D model of the DNA. Later they won the Nobel Prize for the same. So now in the modern era, and this physics is giving like many devices to medical sciences also
advanced layer which over the head. So in my research I will use this tool. So I will be discussing about this how this tool is beneficial for the pain patient. I will quickly discuss about this fibromyalgia disease. So it's basically chronic pain disorder which is like second among after the osteoarthritis, and it is characterized by chronic widespread pain over 18 tender points. Other symptoms include sleep disturbance, anxiety, depression. And American College of Rheumatology gives the criteria for diagnosis of this disease. Behind this disease, the role of again this fibromyalgia, of course, is not well known, but some of the research is saying that because of amplification in the spinal cord and brain, these patients are getting augmented stimulus responses, and they are having that dysfunction in their brain center. In short, if I say in these patients there is increase in pain facilitating pathways and decrease in pain inhibiting pathways. I want to tell you we have in our body, our nervous system is having two kinds of pathways, one pain facilitation. I don't know what is it. Yeah. And there is pain inhibitory pathways. And both these pathways are very useful our daily defense mechanism and day-to-day life activities. Suppose we have pain facilitating pathway, if we have injury at any site, right? So that pain we will feel until we recover that body part, right? And for pain inhibition it works like that. Pain inhibits pain. If we have more intense pain, then we will forget the less pain, less pain. So in these patients, these alterations occur in these brain pathways. Research also suggested that they have some abnormalities in the neurotransmitter levels and hormone levels also. And in these patients, medication provides only symptomatic relief. So in coming years, this magnetic stimulation coming to the picture. Again, which is given this tool to the medical sciences. This basically magnetic stimulator is a non-invasive method of brain stimulation in which magnetic fields are used to induce the electric currents in the cerebral cortex, thereby depolarizing neurons and neuronal networks. Basically, it is based on Faraday's law of electromagnetic induction, which produce magnetic fields in its vicinity, which induce secondary currents in a conducting medium. So, right here. So, when a time varying current is passed through a low electric current is passed through a wire of the coil, which induce a magnetic field perpendicular to this coil, and which in turn induce the electric field in the layer of the brain, and which depolarize the neuron and generate action potentials. So this is the figure of 8 coil. There are two kinds of coil available here, circular and figure of 8. But this is used majorly because it gives a more focused magnetic. fibromyalgia patient, and they were having this significant relief in pain and the related symptoms. So objectives were to study the effect of this magnetic stimulation on subjective and assessment and pain threshold of these patients. So we taken the fibromyalgia patients. This is the exclusion and inclusion criteria. We excluded the patients who were having some pacemaker or lactating mothers or who were having some chronic diseases. Yeah, this was basically 6-month protocol. The magnetic stimulation was given for total 4 weeks. Either real treatment or sham or placebo effect. I sure you have heard about placebo or sham treatment. So around 50% of the patients were given the real TMS stimulation and 50% given were like dummy or fake kind of stimulation. Just to actually know the effect of the stimulus. And then the patients were followed up for the 6 months at 3 time points. Subjective assessment of pain was done with the help of some specific questionnaire, and then objective assessment was done with nociceptive flexion reflex. What is this flexion reflex? It was recorded at the biceps femoris muscles. This is the actual recording from the lab. This is the EMG response. And this is recorded from the biceps femoris muscle. The sural muscle, sural nerve response is calculated. This I will show you. Once.
Yeah.
So, how we give you this TMS? First, we decided some frequency or some points. Like we have selected our area that is dorsolateral prefrontal cortex, right? So, how we mark that area on every patient? So, for that, first we need to get the resting motor section, which is a marker of measure of cortical excitability of every person. So, first we determine that. Excitability. So for that, what we did, we found the cortex midpoint between AGO and EO, and then around 5 centimeter later to that point there is probability of finding the area. Actually, we for finding the total threshold, we check the in this way, we check the movement of the abdominal brevis muscles. Like similar movement we found. We mark the area of the marker, and then for 5 centimeter anterior parasagittal line, we mark our area that is dorsolateral prefrontal cortex for giving the stimulation. This I showed all you aware about. We use low frequency, that is 1 hertz. 1 hertz means in 1 second, 1 pulse was given. 5 hertz means 5 pulses in 1 second. So we use low frequency TMS. So this is the protocol for use for all patients. Yeah. in pain ratings in the patients. But I was telling you that there was a real stimulator, magnetic coil, and there was a sham coil. It is similar to placebo. There is a difference between placebo and sham. Placebo means we use some substance like sugar or other, and sham means like we put fake devices or dummy utensils. So we have 2 coils with us. Obviously, patients were not aware about that. They were not getting any kind of treatment. They were blinded for the study. So 50% patient got this actual stimulation, and 50% patients received the sham stimulation, dummy or fake kind of stimulation. So at the end of the study, what we found was there was decrease in pain ratings and associated symptoms were also decreased. So we propose a mechanism of light PFC PMS in these ways. So this brain area is related to other brain area, not telling me like this. Why these patients were having release in pain and related symptoms? Because this area is related to other brain areas which are involving in the emotional aspects of pain. That is why they are having decrease in the pain and the associated symptoms. So yeah, high frequency, low frequency TMS both are effective in treatment of this fibromyalgia, not only fibromyalgia but other chronic pain disorders also. Although it is useful and safe treatment options, but something which we need to keep in mind, the type of coil also have orientation, distance between brain and coil, magnetic pulse waveform, intensity, pattern and frequency, age, gender, genetic aspects and ongoing treatment. We need to keep in mind these things. Safety and regulations. We also added our research investigator fibromyalgia and magnetic stimulation. So we also published our proposed mechanism through this paper. Before this, I want to convey that in 8 hospitals, this treatment is given free of cost. But if we go in the private hospitals, they used to collect per session 3,000 to 7,000 rupees. They depend on the type of disease or the requirement. So I just wish all people should be healthy, but if anyone having their relative, better they should go to AIDS hospital rather than go to the private hospitals. Thank you so much.
इनसे सब कुछ ही फ्री है सारे कैंसर के लिए अच्छा साला नंबर दिक्कत तो ये है कैंसर और काफ़ी सेंसिटिव डिजीज में तो अच्छा है ऑनलाइन नंबर आ जाता
Is that using magnetic waveform for treatment or for detection only?
Treatment, sir.
Treatment only?
Yes, sir.
So how much magnetic field will be applying for that?
So that is depend on the output of the device. So that I will show you the video, sir. Like we are taking the motor protect excitability of the patient, and then accordingly, sir, we are designing like how much the patient.
How much magnetic field is required to detect the disease? That is
So this is for not for, as I am saying, it is for treatment, not for.
So you decide on the basis of gravity of the disease that how much magnetic field you have to.
So different frequencies are given, so like 1 Hz, 2 Hz, 5 Hz. So there is literature beyond that. Which frequency should be given to which kind of disease or disorder? Like for depression, different kind of frequency are given for headache patient, different kind of frequency. Some patients get relief on the high frequency dose, some are get on low frequency.
You have already carried out clinical trials for that?
Yes, sir. It is approved by the slide and semester. US Food Drugs and Administration approved this in 2008 for the patients. So because these pain patients, they are not having relief from any kind of medication. Like they are having symptomatic
sound is also there, like MRI.
Yes, sir.
Some kind of sound you see while
So not that much sound. Sir, MRI produces very technical sound, sir.
you cannot sit there.
So I personally don't have that bad experience, but I know. So nowadays, this TMS neural aggregated here. So to get the accurate side of like stimulation.
You are not changing the magnetic field strength, only frequency you are changing.
Yes, sir.
That means there should be a minimum threshold.
Yes, that we find it for every person. So for every person it can be different, sir. Like we are taking fixed frequency, like at 1/3 feet only our breath. Sir, it generates, so it's a magnet, that device output, sir. We are giving the electric current, sir, that producing the magnetic field.
I agree. It is a device output, but there should be some magnetic field.
So that I
Whereas he's asking, there must be some threshold heat also. You are changing frequency of that because you are changing.
So we have given like the electric current to the pole. That generates the magnetic field, sir. That I need to check further. We are because we just check on other things, not the physics other things.
Thank you, Dr. Simon, for the excellent work and presentation. I have few announcement before I use the sleep on lunch. Firstly, I felicitate Dr. Suman for the presentation.
Thank you.